Since the dawn of human consciousness, we have gazed upward at the night sky, wondering if we are alone in this vast universe. This timeless question has evolved from ancient mythology and philosophical ponderings to modern scientific inquiry. Today, as our technological capabilities expand, we stand at a remarkable moment in this quest, actively searching not just for simple life, but for the technological footprints of advanced civilizations beyond Earth. Throughout human history, we have imagined what extraterrestrial beings might look like, how they might think, and whether they too gaze up at their skies wondering about us. But in recent decades, scientists have turned this age-old wondering into methodical investigation, developing increasingly sophisticated methods to detect what we now call techno-signatures, the technological fingerprints that might reveal the presence of intelligent life elsewhere in the cosmos. When we consider the immensity of our galaxy alone, with its estimated 400 billion stars, and the broader universe containing trillions of galaxies, the mathematical probability suggests we should not be alone. Yet, as physicist Enrico Fermi famously asked, if intelligent life is common, where is everybody? This apparent contradiction between probability and observation forms the heart of what we now call the Fermi paradox, a puzzle that continues to intrigue scientists and dreamers alike. In this gentle exploration, we will journey through the methods astronomers and researchers use to search for signs of technology beyond Earth. From massive radio telescopes scanning the skies for artificial signals, to orbital observatories searching for the shadows of vast alien megastructures, to spectrometers analyzing distant atmospheres for industrial chemicals, humanity has deployed remarkable tools in this search. The quest to find techno-signatures represents something profound about our species. It speaks to our curiosity, our desire to connect, and our capacity to imagine possibilities beyond our immediate experience. Even if we never detect a clear signal from another civilization, the search itself expands our understanding of the universe and our place within it. As night falls across our planet, teams of scientists at observatories around the world aim their instruments toward the stars. Massive dishes turn silently, computers process petabytes of data, and researchers scan results for patterns that might indicate something beyond natural phenomena. This persistent listening has continued for decades, through changing technologies and shifting paradigms, yet always with the same fundamental question: are we alone? The answer remains elusive, but the questions themselves have evolved with growing sophistication. We now understand that searching for life beyond Earth requires nuance and creativity. Different civilizations might utilize technologies we cannot yet imagine. They might communicate in ways we have not considered. They might exist in places or forms we have not thought to look for. Consider the progress of our own civilization. In just the past century, we have moved from the first radio transmissions to quantum communication, from basic flight to space exploration. Our technological evolution has been exponential, and if other civilizations follow similar trajectories, they might be using communication methods far beyond our current understanding. This realization has expanded our search methodologies, pushing us to look not just for signals like our own, but for any anomaly that might indicate artificial origin. The challenges are immense. Space is vast and largely empty. Signals diminish with distance. Natural phenomena can mimic artificial ones. And perhaps most significantly, we cannot know the minds or motivations of beings we have never encountered. Would they wish to communicate? Would they broadcast their presence? Or might they choose to remain silent, watching the cosmos from their own quiet corner? These questions touch not just on astronomy and physics, but on biology, psychology, philosophy, and even spirituality. The search for techno-signatures is interdisciplinary by necessity, requiring us to think across boundaries and beyond our familiar frameworks. As we drift through sleep listening to this exploration, we might consider how the very act of searching connects us to a long human tradition. From early seafarers navigating by stars to modern astronomers mapping distant galaxies, we have always sought to know what lies beyond the horizon. The search for techno-signatures represents the furthest extension of this impulse, reaching not just across oceans or continents, but across the vast emptiness between stars. In 1977, humanity launched the Voyager spacecraft, carrying golden records with sounds and images from Earth. These artifacts continue their journey outward, now beyond the boundaries of our solar system, silent ambassadors carrying our story into the void. This gesture, both scientific and deeply poetic, represents our longing not just to discover others, but to be discovered ourselves. The golden records were designed to last for billions of years, far longer than many of our terrestrial monuments. They contain greetings in 55 human languages, sounds of Earth from thunderstorms to whale songs, and music from diverse cultures. Though the chances of interception are astronomically small, their creation speaks to a profound hope that somewhere, someone might one day hold this artifact and understand something about us. As we search for techno-signatures from other worlds, we might imagine similar objects sent by other civilizations, drifting through space, carrying stories we cannot yet comprehend. Perhaps they take forms we would not recognize as communication, encoded in ways that reflect minds and motivations vastly different from our own. The night sky holds not just scientific mysteries, but existential ones. Each point of light represents a potential story, a possible history of evolution and development that might parallel our own or diverge in ways we cannot imagine. When we search for techno-signatures, we are really asking, are there others who have faced the same challenges we face? Have they found solutions? Have they endured long enough to reach beyond their home world? In the quiet moments of pre-dawn, when most of humanity sleeps and the stars shine with particular clarity, radio telescopes continue their patient listening. Automated systems scan frequencies, looking for signals that stand out from the cosmic background radiation. And though decades have passed without a confirmed detection, the search continues with steady determination, fueled by the profound implications of success, however unlikely. So let us begin this quiet contemplation of humanity's greatest listening project. In the gentle darkness between stars, in the silent spaces that stretch across light years, we search for whispers of technology, for evidence that somewhere, somehow, others have also looked up at their night skies and wondered about the possibility of us. In the quiet darkness of space, life might reveal itself in many ways. When scientists search for signs of life beyond Earth, they generally look for two distinct categories of evidence, each telling a different story about potential extraterrestrial existence. The first category, known as biosignatures, encompasses the chemical and physical signs of life itself, the biological processes that might be detected across interstellar distances. The second category, which forms the focus of our exploration, is techno-signatures, the detectable evidence of technology created by intelligent life. To understand techno-signatures, we must first distinguish them from their biological counterparts. Biosignatures include chemicals like oxygen, methane, or other compounds that, in certain combinations and contexts, suggest biological activity. They might indicate the presence of microbes, plants, or other life forms altering their environment through metabolic processes. When we study the atmospheres of distant planets and find unusual chemical balances, we might be detecting the breath of alien biospheres, the cumulative exhalation of countless organisms. Techno-signatures, in contrast, represent something fundamentally different, the artifacts and emissions of technological civilization. They are the evidence not just of life, but of intelligence that has developed the capability to significantly modify its environment through engineering and industry. While biosignatures might tell us that a planet hosts life, techno-signatures would tell us that somewhere, somehow, beings have asked questions about their universe and built tools to explore it. The concept was formally introduced to scientific literature in the late 1960s by scientists like James Elliott and Freeman Dyson, though the fundamental idea had been circulating for years before. The term itself, technosignature, has gained widespread usage more recently, becoming a unifying concept for various types of evidence we might detect from technologically advanced civilizations. What specific forms might these technological fingerprints take? The possibilities range from the familiar to the nearly unimaginable, reflecting both our current understanding of physics and more speculative concepts. Radio signals represent perhaps the most widely recognized potential technosignature. Since the early 20th century, human civilization has been broadcasting radio waves into space, creating an expanding bubble of transmission, currently about 100 light-years in radius. These signals, from early television broadcasts to radar pulses, were not intentionally sent as messages to extraterrestrial civilizations, but they nevertheless announce our technological presence to anyone with sensitive enough receivers within that growing sphere. Similarly, other civilizations might produce their own unintentional radio emissions, creating patterns that stand out from the natural background radiation of space. Unlike natural radio sources, which typically produce signals across broad frequency ranges with certain characteristic features, technological transmissions often concentrate energy in narrow frequency bands, creating distinctive spikes in the electromagnetic spectrum. When radio astronomers detect unusually narrow band signals or patterns that appear to carry information, they might be observing the communications or technological emissions of another civilization. Intentional radio messages represent another possible technosignature. In 1974, humanity sent its first deliberate message to the stars using the Arecibo radio telescope in Puerto Rico. This transmission, directed towards the globular cluster M13 approximately 25,000 light-years away, encoded basic information about human biology, chemistry, and our position in the solar system. While this particular message will not reach its destination for millennia, it represents the type of deliberate communication other civilizations might also attempt. Beyond radio waves, optical signals offer another potential technosignature. Powerful lasers could be used to send concentrated beams of light between star systems, providing a higher bandwidth and more directed form of communication than radio. The advantage of laser communication lies in its focus, allowing transmissions to remain coherent over vast distances without dispersing as rapidly as radio signals. Astronomers search for unusual pulses of light or specific wavelength patterns that might indicate artificial laser transmissions from distant stars. Another intriguing category of technosignatures involves large-scale engineering projects that might be visible across interstellar distances. The most famous conceptual example is the Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson suggested that sufficiently advanced civilizations would eventually harness all available energy from their host star by surrounding it with a swarm of energy-collecting structures. Such a megastructure would intercept and utilize most of the star's energy output, causing detectable changes in the star's observed brightness and spectral characteristics. A complete Dyson sphere might appear to us as an infrared source, radiating waste heat, but unusually dim in visible wavelengths, as the enclosing structure captures most of the star's light. Partial constructions, sometimes called Dyson swarms, might cause unusual fluctuations in starlight as components orbit, creating distinctive patterns of dimming that differ from those caused by transiting planets or natural stellar phenomena. Astronomical observations have identified several stars with unusual light curves, including the now famous case of Tabby's star, formerly designated KIC 8462852, which has exhibited strange, irregular dimming patterns that initially defied conventional explanation. While natural explanations involving dust clouds have gained acceptance for this particular case, the methods developed to study such anomalies continue to be applied in the search for potential artificial structures. Beyond these relatively clear examples, technosignatures might also include atmospheric modifications. As our own civilization has demonstrated, industrial activity can dramatically alter a planet's atmospheric composition. The presence of synthetic chemicals, significant concentrations of carbon dioxide or methane beyond natural equilibrium levels, or other industrial pollutants, could potentially be detected in exoplanet atmospheres through spectroscopic analysis, suggesting the presence of technological activity. Chlorofluorocarbons, nitrogen dioxide, and other industrial compounds have no major natural sources and persist in atmospheres for long periods, making them potential markers of technological civilization. Future space telescopes may be capable of detecting such compounds in the atmospheres of planets orbiting nearby stars, providing evidence not just of life, but of industrial civilization. Even more exotic possibilities include artificial light on night sides of planets, urban heat islands detectable in infrared observations, or artificial changes to planetary surfaces that might be visible during different orbital phases. A civilization that has significantly altered its planet's surface with agriculture, urban development, or other large-scale projects might create reflectivity patterns distinct from those of naturally evolving worlds. Some researchers have even suggested searching for evidence of interstellar spacecraft, such as light sails propelled by lasers or other propulsion systems, that might create distinctive optical or radio signatures as they traverse space. The recent interstellar objects passing through our solar system, such as Oumuamua discovered in 2017, have sparked scientific debate about how we might distinguish natural interstellar travelers from potential artificial probes. Nuclear energy represents another potential techno-signature. The use of nuclear fission or fusion might create detectable isotope ratios or waste products observable in planetary atmospheres. Some researchers have even suggested looking for evidence of nuclear detonations, which would produce distinctive electromagnetic pulses and atmospheric effects potentially observable from great distances. One particularly speculative but intriguing category involves gravity manipulation. If extremely advanced civilizations developed methods to manipulate gravity or space-time itself, such technologies might create observable distortions or anomalies detectable through gravitational wave observatories or precise astrometric measurements. What makes the search for technosignatures so compelling is that while biosignatures might tell us that we are not alone in hosting life, technosignatures would tell us something far more profound, that somewhere else in the cosmos, beings have developed the capacity for abstract thought, scientific inquiry, and technological creation. Such a discovery would provide evidence not just of life, but of minds potentially capable of asking the same questions we ask about the universe. The search for technosignatures also offers certain advantages over biosignatures from a detection standpoint. Technological signals can be designed or incidentally created in ways that stand out clearly from natural background processes. A narrow-band radio signal or laser pulse is instantly distinguishable from natural phenomena, whereas some biosignatures might be mimicked by non-biological processes, creating ambiguity in interpretation. Additionally, technology can potentially operate at energy scales far exceeding biological processes alone. While the biological activity of an entire planet might subtly alter its atmospheric chemistry, technological activity could produce signals visible across much greater cosmic distances. A civilization harnessing even a fraction of its star's energy could create evidence detectable across thousands of light years. However, this search comes with significant challenges. Perhaps the most fundamental limitation involves our own technological framework and imagination. We necessarily search for technologies we can envision and detect, which may represent only a small subset of what advanced civilizations might actually develop. Our search is inevitably shaped by anthropocentric assumptions about how technology evolves and what forms it might take. Consider how rapidly our own technology has transformed within just the past century. From the first radio transmissions to quantum communications, from early computing to artificial intelligence, the trajectory has been not just of incremental improvement, but of paradigm shifts into entirely new technological domains. A civilization, even a few hundred years ahead of our own, might utilize technologies we cannot yet conceptualize, creating techno-signatures we would not know to look for or could not distinguish from natural phenomena. This limitation leads to what some researchers call the temporal coincidence problem. For us to detect another civilization through its techno-signatures, both our technological development would need to overlap not just in space, but in time. Given the age of the universe, approximately 13.8 billion years, and the relatively recent emergence of human technology, this temporal window may be extremely narrow unless technological civilizations typically persist for millions of years or longer. Furthermore, as civilizations advance, they might become more energy efficient or develop technologies that minimize detectable emissions. Our own radio leakage, for instance, has actually decreased in recent decades as we have shifted to cable, fiber optics, and directed satellite communications rather than powerful broadcast transmitters. An advanced civilization might become effectively invisible, not because it has disappeared, but because its technology has evolved toward greater efficiency and reduced waste emissions. Some researchers have also suggested that advanced civilizations might deliberately conceal their techno-signatures, either to conserve energy or for security concerns, creating a cosmic version of a silent forest where intelligent life exists but chooses not to broadcast its presence widely. Despite these challenges, the search for techno-signatures represents one of humanity's most profound scientific endeavors. It combines cutting-edge astronomy, signal processing, artificial intelligence, and speculative thinking about the nature of technology and intelligence itself. Whether successful or not in its primary goal, this search has already advanced our understanding of the cosmos and pushed the boundaries of multiple scientific disciplines. The field continues to evolve with new detection capabilities, theoretical frameworks, and search methodologies. Machine learning algorithms now sift through astronomical data looking for patterns that might elude human observers. Space-based telescopes provide ever more detailed observations of exoplanets. Radio observatories scan the skies with increasing sensitivity across wider frequency ranges. In essence, techno-signatures represent the most definitive evidence we could discover of intelligent life beyond Earth. While a confirmed biosignature would revolutionize our understanding of life in the universe, a verified techno-signature would transform our understanding of intelligence, technology, and our place in the cosmic community of minds. It would tell us not just that we are not alone in harboring life, but that we are not alone in wondering, questioning, and building tools to extend our reach beyond our home planet. As we continue our exploration of various types of techno-signatures and the methods used to search for them, we carry with us this fundamental understanding that each telescope pointed toward the stars and each algorithm analyzing the resulting data represents humanity's collective reaching out, our patient listening for echoes of minds that might, in fundamental ways, resemble our own. The story of humanity's deliberate search for extraterrestrial intelligence begins, like many scientific endeavors, with a moment of theoretical insight, followed by the patient work of turning speculation into methodology. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a paper in the journal Nature titled Searching for Interstellar Communications. In this landmark publication, they proposed something revolutionary, that radio telescopes had become sensitive enough to detect signals from civilizations around nearby stars, if such civilizations existed and were transmitting with similar technology to our own. Their paper opened with a sentence that would define the field. The probability of success is difficult to estimate, but if we never search, the chance of success is zero. With this simple yet profound statement, they established the philosophical foundation for what would become known as the search for extraterrestrial intelligence, or SETI. Cocconi and Morrison suggested focusing on a specific radio frequency of 1,420 MHz, corresponding to the emission line of neutral hydrogen, the most abundant element in the universe. They reasoned that this frequency would be known to any technically advanced civilization and might serve as a logical channel for interstellar communication, a cosmic meeting place in the electromagnetic spectrum. This concept of universal frequencies that might be chosen for communication across the vast distances of space would become a guiding principle in early SETI efforts. Shortly after this theoretical proposal, a young radio astronomer named Frank Drake conducted the first practical search for artificial signals from beyond our solar system. In the spring of 1960, Drake aimed the 85-foot radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. This project, which Drake named Project Ozma, after the queen of the fictional Land of Oz, marked the birth of observational SETI. For several weeks, Drake and his small team monitored these stars across a narrow band of frequencies near the hydrogen line, looking for any signals that might stand out from the natural background radiation of space. Though Project Ozma detected no artificial signals during its brief operation, it established both the technical methodology and scientific legitimacy of Radio SETI. The silent receivers represented humanity's first deliberate act of cosmic listening, our first conscious attempt to detect the technological fingerprints of another civilization. 1 year after Project Ozma, in 1961, Drake organized a small, informal conference at Greenbank to discuss the prospects for detecting extraterrestrial intelligence. In preparation for this meeting, he developed what became known as the Drake equation, a probabilistic formula attempting to estimate the number of communicative civilizations in our galaxy. The equation multiplied 7 factors, beginning with the rate of star formation and proceeding through the fraction of stars with planets, the number of habitable worlds per planetary system, the fraction of those worlds where life emerges, the fraction of life that evolves intelligence, the fraction of intelligent species that develop detectable technology, and finally, the average longevity of such technological civilizations. While the equation provided no definitive answers, it offered a structured framework for thinking about the problem and highlighted our profound ignorance regarding several key parameters. The final term, regarding the longevity of technological civilizations, emerged as particularly significant. If such civilizations typically survive for millions of years, the galaxy might host numerous concurrent communicative species. If, however, technological civilizations tend to quickly self-destruct or abandon detectable communications, we might inhabit a largely silent galaxy despite the potential abundance of life. The Drake equation remains influential not because it solved the question of extraterrestrial intelligence, but because it transformed a philosophical speculation into a scientific inquiry with specific, potentially measurable parameters. It helped legitimate SETI as a scientific field rather than merely a speculative enterprise. Throughout the 1960s and early 70s, Radio SETI remained a small-scale effort conducted by individual scientists, often using existing astronomical facilities during limited allocated time. The Soviet Union also began SETI programs during this period, with astronomers like Nikolai Kardashev developing influential theoretical frameworks regarding the energy usage of advanced civilizations. A significant shift occurred in 1971 when NASA funded a small study called Project Cyclops, led by Bernard Oliver and John Billingham. The resulting report proposed an ambitious array of 1,000 radio telescopes dedicated to SETI, a project that would have cost billions of dollars. While Cyclops was never built, the detailed engineering and scientific work conducted for the study established design principles that would influence SETI research for decades to come. The 1970s also saw the first dedicated SETI programs at major observatories, including the Ohio State University's Big Ear Radio Telescope. This continuous survey of the sky led to perhaps the most famous moment in SETI history, the detection of the so-called WOW signal on August 15, 1977. The WOW signal, named for the annotation made by astronomer Jerry Amon when reviewing the computer printout of the data, was a strong, narrow-band radio signal detected at a frequency near 1,420 MHz, precisely the region of the spectrum where Cocconi and Morrison had suggested looking for extraterrestrial transmissions. The signal lasted for the full 72 seconds that the telescope's receiver remained pointed at its location and displayed characteristics consistent with an artificial source rather than natural radio emission. Despite extensive follow-up observations of the same region of sky, the signal was never detected again. the WOW signal remains one of the most tantalizing potential techno signatures ever recorded, conforming to many expected characteristics of an extraterrestrial transmission, yet lacking the repeatability that would allow definitive classification. It serves as both an inspiration for continued searching and a reminder of the methodological challenges in distinguishing a genuine techno signature from a one-time anomaly or unrecognized terrestrial interference. The 1980s saw increased institutional support for SETI, culminating in 1992 with the launch of NASA's High-Resolution Microwave Survey, a comprehensive program that would have conducted both targeted searches of nearby stars and all-sky surveys using multiple radio observatories. However, just 1 year after its commencement, congressional action terminated NASA's SETI funding, with Senator Richard Bryan famously declaring that not a single Martian had been discovered despite millions spent. This political setback led to a fundamental restructuring of SETI efforts in the United States. The NASA program was privatized, evolving into the SETI Institute, a non-profit research organization that would continue the scientific mission without government funding. The Institute's Project Phoenix carried forward the targeted search component of the NASA program throughout the 1990s and early 2000s, eventually observing over 800 nearby star systems with unprecedented sensitivity and frequency coverage. Meanwhile, other approaches to radio SETI emerged. The Serendip program at the University of California, Berkeley, developed a novel piggyback approach, attaching specialized SETI receivers to existing radio telescopes to analyze data simultaneously with conventional astronomy observations, effectively getting SETI for free in terms of telescope time. This parasitic approach reached its most public expression with the launch of SETI at Home in 1999, a distributed computing project that allowed ordinary people to contribute their personal computer's processing power to analyze SETI data. At its peak, millions of participants worldwide were processing data chunks downloaded from Berkeley's servers, creating what was effectively the world's largest supercomputer dedicated to the search for extraterrestrial intelligence. The concept of distributed and citizen science approaches to SETI represented an important democratization of the field, transforming the search from a specialized scientific niche into a global collaborative endeavor. It also reflected the growing computational demands of modern SETI, as increasing receiver sensitivity and bandwidth generated data volumes that exceeded the processing capabilities of many traditional computing facilities. The early 21st century brought a significant new entrant to radio SETI with the Allen Telescope Array, funded primarily by Microsoft co-founder Paul Allen. This pioneering facility in Northern California was designed specifically with SETI as a primary science driver, featuring a novel design of many small dishes rather than a few large ones, allowing for flexible and simultaneous observation of multiple target stars. While financial challenges have limited the Allen Telescope Array to a fraction of its planned size, it represents an important step toward dedicated SETI instrumentation, rather than borrowed time on general-purpose astronomical facilities. The array continues to conduct observations today, scanning nearby stars across billions of frequency channels simultaneously. The modern era of radio SETI has been characterized by both increased technical capability and greater integration with mainstream astronomy. The launch of the Breakthrough Listen initiative in 2015, funded with $100 million from Russian-Israeli entrepreneur Yuri Milner, represented the largest investment ever in the search for techno signatures. This program utilizes approximately 25% of the observation time on some of the world's largest radio telescopes, including the 100-meter Green Bank telescope in West Virginia and the 64-meter Parkes telescope in Australia. Breakthrough Listen examines thousands of nearby stars and 100 galaxies across billions of frequency channels, with sensitivity to signals millions of times weaker than previous SETI programs could detect. The initiative also incorporates optical SETI, searching for potential laser communications, and employs advanced machine learning algorithms to identify promising signals among the enormous data volumes generated. Throughout this history, Radio SETI has confronted several fundamental challenges that continue to shape the field. Perhaps the most significant is the needle in a haystack problem. The need to distinguish potential artificial signals from both natural cosmic radio sources and human-generated interference. As our own technological civilization has expanded its radio frequency usage, particularly with satellite communications, the task of filtering out terrestrial signals has become increasingly complex. Modern SETI efforts employ sophisticated algorithms to identify signals that display characteristics unlikely to occur naturally, such as narrow frequency bandwidth, drift rates consistent with planetary motion, or temporal patterns suggesting encoded information. Multiple observations of the same target with different telescopes or at different times can help distinguish local interference from genuine cosmic signals, as terrestrial sources would typically appear in only one receiver, while a distant signal would be detectable from multiple locations on Earth that have the target in view. Another persistent challenge involves the question of where to look and at what frequencies. The electromagnetic spectrum is vast, and monitoring the entire sky across all possible frequencies would require resources far beyond current capabilities. SETI researchers must therefore make strategic choices about target selection and frequency coverage based on theoretical considerations about the nature of potential transmitters. Target selection has evolved significantly over SETI's history. Early programs focused primarily on nearby Sun-like stars, reasoning that planets around such stars might host life similar to Earth's. As our understanding of exoplanets has expanded, target selection has grown more sophisticated, incorporating factors such as known planet-hosting stars, habitable zone planets identified by transit missions like Kepler, and even globular clusters, where advanced civilizations might find dense stellar environments advantageous for interstellar communication or travel. Some researchers have advocated for monitoring the entire sky rather than selected targets, arguing that transient signals might be missed by intermittent observations of specific stars. Others have suggested focusing on the galactic plane or center, where the greatest concentration of stars would provide the highest probability of success if advanced civilizations are rare but visible across great distances. The question of frequency selection presents similar trade-offs. While early SETI focused on the region around the hydrogen line at 1420 MHz, sometimes called the cosmic waterhole due to its proximity to emission lines of hydrogen and hydroxyl, modern receivers can cover much broader bands simultaneously. Breakthrough. Listen, for instance, scans billions of channels across gigahertz of bandwidth, significantly increasing the chance of detection if transmissions exist outside the historically favored frequency ranges. Beyond these tactical considerations, Radio SETI confronts deeper questions about the nature of potential transmitters. Would advanced civilizations deliberately broadcast their presence, or would we be limited to detecting their unintentional leakage radiation? If deliberate broadcasts exist, would they be omnidirectional beacons announcing their presence to the galaxy at large, or directed transmissions between specific star systems that we might intercept only by chance? Our own civilization's radio emission profile has evolved significantly over just a century of technological development, from high-power omnidirectional broadcast technologies in the early 20th century to increasingly efficient, directed and encrypted communications today. This evolution suggests that the window during which a civilization produces easily detectable radio emissions might be relatively brief, adding a temporal challenge to SETI's spatial and frequency search space. Despite 6 decades of increasingly sophisticated searching, Radio SETI has not yet detected a confirmed Techno signature. This absence of detection has been interpreted in various ways, from the suggestion that technological civilizations must be exceedingly rare, to the possibility that advanced technologies evolve beyond radio communications relatively quickly, to more exotic proposals such as self-imposed silence for security reasons, or the existence of a galactic communication network that we have not yet discovered how to access. Yet the history of Radio SETI is not a story of failure, but of persistent questioning and methodical exploration. Each silent observation constrains our understanding of the possible distribution and nature of technological civilizations, Each new search pushes our technical capabilities forward, developing methodologies and technologies with applications beyond SETI itself. Radio astronomy was once described as the study of the universe through impossible eyes, perceiving light in wavelengths invisible to human biology. Radio SETI represents a further extension of this metaphor, not just studying the natural universe through these impossible eyes, but specifically searching for patterns that would indicate other minds, other technologies, other civilizations, asking their own questions about the cosmos. As radio telescopes around the world continue their patient listening, as data processing algorithms become increasingly sophisticated in identifying anomalous signals, the classic search continues. Each observation carries the possibility, however remote, of answering one of humanity's oldest questions: are we alone? While radio waves have dominated the search for extraterrestrial intelligence since its inception, another region of the electromagnetic spectrum offers compelling advantages for interstellar communication. Visible light and its nearby wavelengths have increasingly attracted the attention of SETI researchers, opening a complementary avenue in the search for techno signatures. This approach, known as optical SETI, focuses on detecting potential laser signals from distant civilizations, artificial flashes of light that might carry messages across the vast distances between stars. The concept of optical SETI emerged largely from advances in our own laser technology. In 1961, just 1 year after the invention of the first functional laser, astronomer Robert Schwartz and Nobel Prize-winning physicist Charles Townes published a paper proposing that lasers could serve as effective tools for interstellar communication. Their calculations suggested that even with the primitive laser technology of that era, a sufficiently powerful beam could outshine a sun-like star when concentrated into a narrow frequency and directed precisely toward a target. This fundamental insight, that artificially generated light could potentially stand out against the broad spectrum background of stellar radiation if sufficiently concentrated in wavelength, direction, and time, established the theoretical foundation for optical SETI. However, practical searches would not begin for several decades, as both the technology to generate and detect such signals needed time to mature. Unlike radio waves, which naturally propagate in all directions from their source, light can be focused into extremely narrow beams, allowing the energy of the transmission to remain concentrated over interstellar distances. This property makes lasers particularly suited for directed communication, where the sender targets specific star systems rather than broadcasting omnidirectionally. The mathematics of interstellar laser communication reveal its potential efficiency. A moderate-sized 1-meter optical telescope paired with a 1-kilowatt laser, technology well within our current capabilities, could create a signal detectable by similar equipment at distances exceeding 1,000 light-years, if precisely aimed. More advanced technology could extend this range significantly, potentially allowing communication across much of the galaxy with reasonable energy expenditure. This directional nature creates both advantages and challenges for SETI researchers. The advantage lies in signal strength, as the concentrated energy of a laser pulse might be more easily distinguished from background light than a radio signal from a similar power source. The challenge, however, is that we would only detect such signals if they were specifically directed toward our solar system, or if we happened to cross the path of a transmission between other star systems. The first systematic optical SETI observations began in the late 1990s, with programs at Harvard University, the University of California's Lick Observatory, and Princeton University. These early efforts used photomultiplier tubes capable of detecting brief pulses of light, searching for signals that might last only billionths of a second, far shorter than any known natural optical phenomena from astronomical sources. The Harvard Optical SETI program, led by Paul Horowitz and colleagues, examined thousands of nearby stars using a dedicated 61-centimeter telescope equipped with specialized detectors. The system was designed to identify simultaneous bursts of light at multiple wavelengths, a signature that would help distinguish artificial signals from random detector noise or atmospheric effects. Despite surveying over 15,000 star systems between 1998 and 2003, no unambiguous laser signals were detected. Concurrent with Harvard's targeted search, the University of California's Lick Observatory conducted observations using its 1-meter nickel telescope. Rather than searching for brief pulses, this program focused on detecting continuous laser emissions within the spectra of stars. The approach relied on the fact that lasers emit light at extremely precise wavelengths, creating narrow spectral lines that would stand out from the broader absorption and emission features in a star's natural spectrum. These pioneering programs established the technical feasibility of optical SETI, but faced significant limitations in their coverage of both the sky and the full range of possible signal types. Like early radio SETI, initial optical searches could monitor only a small fraction of potential targets and wavelengths, constrained by available technology and observing time. The early 2000s saw important advances in optical SETI capability. The development of fast photon counting detectors and the application of optical fiber technology allowed for more sensitive and comprehensive searches. At Harvard, the earlier targeted program evolved into a dedicated all-sky optical SETI survey using a 1.8-meter telescope specifically constructed for this purpose. This system, operational from 2006, could monitor the entire visible northern sky, addressing the limitation that narrowly directed laser beams might be transient or aimed at locations other than specific target stars. Meanwhile, the 7-dip optical SETI program at the University of California, Berkeley implemented a novel approach using the historic 1-meter nickel telescope at Lick Observatory. This system split incoming light into multiple channels observed by separate detectors, allowing the identification of signals that appeared simultaneously in different wavelengths, a characteristic expected of some artificial transmissions, but unlikely in natural phenomena. As technology advanced, so did the sensitivity and scope of optical SETI. The Berkeley program eventually evolved into the Near-Infrared Optical SETI project, expanding the search into wavelengths invisible to the human eye, but potentially advantageous for interstellar communication. Near-infrared light experiences less scattering and absorption from interstellar dust than visible wavelengths, potentially making it a preferred region of the spectrum for civilizations wishing to communicate across significant portions of the galaxy. The past decade has seen optical SETI enter a new phase of integration with mainstream astronomy through the application of existing astronomical instrumentation to the search for laser technosignatures. Large archives of stellar spectra, gathered for conventional astronomical research, have been analyzed for signs of unusually narrow emission lines that might indicate laser activity. The immense databases from sky surveys like the Sloan Digital Sky Survey contain spectral information for millions of objects, providing a rich resource for technosignature searches that require minimal additional observing time. This approach of using archived data for SETI represents an important evolution in the field, leveraging the massive investment in astronomical infrastructure for technosignature research at minimal marginal cost. Similar approaches have been applied to time-domain astronomy, with researchers examining data from surveys that repeatedly observe large portions of the sky, looking for brief flashes or unusual variability patterns that might indicate artificial signals. The Breakthrough Listen initiative, launched in 2015, included optical SETI as a significant component alongside its radio observations. Using instruments like the automated Planet Finder telescope at Lick Observatory, this program conducts spectroscopic observations of target stars, searching for laser lines embedded within their spectra. The initiative's significant funding has enabled longer observation times and greater sensitivity than previous optical SETI efforts, though still covering only a fraction of possible targets and signal types. One particularly innovative approach to optical SETI involves the search for laser signals used for propulsion rather than communication. In 2016, the Breakthrough Starshot initiative proposed using powerful ground-based lasers to accelerate small light sails to a significant fraction of the speed of light, enabling interstellar travel within a human lifetime. If other civilizations have developed similar technology, the immense power requirements for interstellar laser propulsion systems might create detectable signals far exceeding those of communication lasers. Such propulsion lasers would likely operate at power levels measured in gigawatts or higher, potentially visible across thousands of light years, even if not specifically directed toward Earth. Researchers have suggested monitoring nearby galaxies for brief, intense flashes that might indicate the operation of such systems, expanding optical SETI beyond our immediate galactic neighborhood. The potential advantages of laser communication over radio extend beyond signal strength and directionality. The higher frequencies of optical light allow for greater bandwidth, potentially transmitting more information per second than radio signals. This efficiency might make optical communication the preferred choice for advanced civilizations, particularly for transmitting complex data rather than simple beacons announcing their presence. Additionally, the development of extremely short pulse lasers, operating on timescales of femtoseconds, 1/1,000,000th of 1/1000,000th of a second, opens possibilities for signals that would be nearly impossible to recreate through natural processes. Such brief pulses could encode information while remaining distinct from any known astrophysical phenomena, providing an unambiguous techno signature if detected. Despite these theoretical advantages, optical SETI faces unique challenges compared to its radio counterpart. Earth's atmosphere presents a significant obstacle, absorbing or scattering certain wavelengths of light and creating distortion effects, known as seeing that limit the resolution of ground-based telescopes. Atmospheric turbulence can mimic brief flashes, creating false positives that must be carefully filtered from the data. Weather conditions and the day-night cycle further limit continuous observation, whereas radio telescopes can often operate under cloudy skies and during daylight hours. To address these limitations, some researchers have proposed space-based optical SETI telescopes, free from atmospheric interference and capable of continuous observation. While the cost of such systems has been prohibitive thus far, the decreasing expense of space launches and the development of small satellite technologies may eventually make this approach feasible, particularly as part of multi-purpose astronomical missions that serve conventional science alongside SETI objectives. Optical SETI also confronts the fundamental challenge of the vast parameter space that must be searched. Lasers can operate across a wide range of wavelengths, pulse durations, repetition rates, and modulation patterns. Natural limitations narrow this range somewhat, as certain wavelengths propagate more efficiently through the interstellar medium, and basic information theory suggests optimal encoding methods for noisy channels. Nevertheless, the possible signal types remain numerous, requiring researchers to make strategic choices about which parameters to prioritize in their searches. These choices often reflect assumptions about the motivations and technologies of potential transmitting civilizations. Would they prioritize signals that stand out clearly from natural backgrounds? Or would efficiency and minimal energy expenditure drive their communication strategies? Would they target specific promising star systems or create omnidirectional beacons visible from many potential locations? Would they design signals specifically for ease of detection by emerging technological civilizations, or optimize for communication with peer-advanced societies? Such questions highlight a fundamental aspect of all SETI research, that our search strategies inevitably incorporate assumptions about the nature, motivations, and technological evolution of extraterrestrial intelligence. These assumptions may limit our ability to recognize signals that operate outside our expected parameters, creating potential blind spots in our search. To address this limitation, some optical SETI researchers have advocated for new approaches focused on identifying astronomical observations that cannot be explained through known natural processes, rather than searching for specific anticipated signal types. This agnostic approach seeks anomalies first and considers their potential artificial origins second, potentially opening the search to techno-signatures we have not specifically anticipated. While no confirmed laser techno-signatures have been detected to date, optical SETI has yielded interesting anomalies that warrant further investigation. In 2015, a team analyzing spectral data from 2.5 million stars in the Sloan Digital Sky Survey identified several hundred objects with unusual emission features that could potentially represent laser activity. Follow-up observations of these candidates continue, though many have been explained through rare but natural stellar phenomena or instrumental effects. More recently, projects using fast photometry, the measurement of light intensity at very short time intervals, have detected brief flashes from various locations in the sky. While most such events can be attributed to cosmic rays striking detectors, satellite glints, or atmospheric phenomena, some remain unexplained and continue to be monitored for patterns that might suggest artificial origin. The future of optical SETI appears bright, with new technologies enabling more comprehensive searches across wider parameter spaces. Advances in detector technology, particularly superconducting nanowire single-photon detectors capable of registering individual photons with minimal noise and excellent timing precision, promise to significantly increase sensitivity to brief laser pulses. Large astronomical projects currently under development, such as the Vera C. Rubin Observatory, with its planned legacy survey of space and time, will repeatedly image the entire visible sky with unprecedented depth and cadence. While primarily designed for conventional astronomy, these observations will provide a rich dataset for identifying unusual optical transients that might represent technosignatures. Optical SETI's evolution reflects a broader trend in the search for extraterrestrial intelligence, moving from targeted searches for specific anticipated signal types toward more comprehensive monitoring of the sky for any anomalies that might indicate technological activity. This shift acknowledges both the vastness of the parameter space to be searched and our limited ability to predict the specific technologies and communication strategies of advanced civilizations that may have evolved along very different paths than our own. As with radio SETI, the absence of a confirmed detection in optical SETI thus far tells us something about the prevalence or nature of technological civilizations, but we must be careful in interpreting this silence. Current search capabilities still cover only a tiny fraction of potential targets, wavelengths, and signal types. The directed nature of laser communication means that even widespread interstellar communication networks might remain undetectable unless Earth happens to lie along transmission paths or is specifically targeted. The complementary nature of radio and optical SETI highlights the importance of maintaining diverse approaches in the search for technosignatures. Different wavelengths offer different advantages for interstellar communication, and we cannot know which regions of the electromagnetic spectrum potential extraterrestrial communicators might prefer. By maintaining searches across multiple portions of the spectrum, we increase our chances of detection, regardless of the specific technologies employed by other civilizations. This multispectral approach continues to expand, with researchers now considering potential technosignatures across the entire electromagnetic spectrum, from low-frequency radio waves to high-energy gamma rays. Each region offers unique opportunities and challenges, contributing to a more comprehensive search strategy that acknowledges the vast possibilities for how advanced technology might manifest itself across interstellar distances. Optical SETI reminds us that our search for extraterrestrial intelligence is simultaneously a scientific enterprise and a mirror reflecting our own technological evolution. As our capabilities advance, so too does our understanding of how technology might be detected across the cosmic distances separating potentially habitable worlds. In this ongoing dialogue between technology and detection, between signal and search, we continue our patient observation of the night sky, watching for a flash of light that might represent another world's attempt to reach across the stars. In the quiet darkness of night, when we gaze upward at the stars, we observe pinpoints of light that have followed the same predictable patterns for thousands of years. But what if, among these countless stars, some displayed behaviors that defied natural explanation? What if we detected objects in space so massive, so geometrically precise, or so energetically unusual that they could only be the product of engineering rather than natural processes? This is the premise behind one of the most ambitious categories in the search for technosignatures, the hunt for megastructures built by advanced extraterrestrial civilizations. Unlike the search for radio or optical signals, which focuses on detecting intentional or incidental communications, the search for megastructures seeks to identify the physical artifacts of cosmic engineering. These hypothetical constructions would represent the most visible and long-lasting techno-signatures possible, potentially observable across thousands or even millions of light-years, and persisting for timescales far exceeding the civilizations that created them. The concept of astronomical scale engineering entered scientific discourse largely through the work of physicist Freeman Dyson. In a 1960 paper titled "Search for Artificial Stellar Sources of Infrared Radiation," Dyson proposed a thought experiment that would fundamentally reshape how we think about advanced civilizations and their potential detectability. Dyson reasoned that technological civilizations would face ever-increasing energy demands as they developed. Eventually, he suggested, they would need to harness not just the fossil fuels or nuclear resources of their planet, but the entire energy output of their star. To accomplish this, they might construct a vast swarm of energy collecting structures surrounding their sun, capturing most or all of its radiant energy for technological use. Such a structure, now commonly known as a Dyson sphere or Dyson swarm, would fundamentally alter the observational signature of the star system. The star itself would become partially or completely obscured in visible wavelengths, while the waste heat radiated by the structure would create a bright infrared source. This distinctive spectral signature, visible light diminished while infrared radiation increased, would create an astronomical anomaly potentially detectable across interstellar distances. Dyson's proposal was revolutionary because it suggested we might detect advanced civilizations not through their deliberate communications, but through their inevitable energy infrastructure, the physical manifestation of their technological development. The concept established a new category of potential techno-signatures based on the principle that sufficiently advanced technology would create observable modifications to its astronomical environment. In the decades following Dyson's initial proposal, theorists have expanded upon the concept to envision various forms these megastructures might take. A complete Dyson sphere, a solid shell entirely enclosing a star, would present significant engineering challenges, including structural integrity under enormous gravitational stresses. More practical variations include the Dyson swarm, comprising countless independent satellites orbiting in a cloud around the star, or a Dyson ring or belt concentrated around the stellar equator. Another prominent concept is the Dyson bubble, consisting of stationary satellites using solar sails to hover around the star, balanced between gravity and radiation pressure. Such structures could be built incrementally, beginning with a partial swarm that expands as the civilization's energy needs and construction capabilities increase. Beyond these variations on Dyson's original concept, researchers have proposed numerous other potential megastructures that advanced civilizations might construct. Shkadov thrusters, for instance, would use enormous reflectors to direct a star's radiation asymmetrically, gradually altering the star's trajectory through space and potentially allowing a civilization to steer their entire stellar system over cosmological timescales. Astronomical scale habitats represent another category of potential megastructures. In the 1970s, physicist Gerard O'Neill proposed that advanced civilizations might construct enormous rotating habitats in space, creating artificial living environments far larger than planetary surfaces. Scaled to their ultimate expression, such structures might form ring worlds or band worlds partially encircling a star, or even complete shell worlds providing living area equivalent to millions of Earth-like planets. Perhaps the most speculative megastructure concept is the Matryoshka brain, named after nested Russian dolls. This would consist of multiple Dyson spheres nested within each other, each capturing energy that passes through from the layer below and operating at a lower temperature than the previous layer, maximizing thermodynamic efficiency. Such a structure would essentially transform an entire star system into a vast computer, perhaps hosting digital consciousness or performing computations beyond our current comprehension. The search for such structures presents unique challenges compared to other SETI approaches. Unlike intentional radio or light signals, which might be designed for detectability, megastructures would be built for practical purposes rather than communication. Their detectability would be an incidental consequence of their function, making their observational signatures potentially more subtle and ambiguous. Historically, searches for Dyson spheres have focused on identifying infrared excesses, stars that emit more infrared radiation than expected based on their visible light output. Several surveys have been conducted using data from the Infrared Astronomical Satellite, the Wide Field Infrared Survey Explorer, and the Spitzer Space Telescope, looking for objects with unusual spectral energy distributions consistent with partial or complete stellar enclosure. These surveys have identified numerous anomalous infrared sources, warranting further investigation, though most have been attributed to natural phenomena such as dust-shrouded stars or certain types of variable stars rather than artificial structures. The ambiguity highlights a persistent challenge in the search for megastructures, distinguishing truly artificial constructions from rare but natural astronomical objects that may mimic some of their characteristics. In 2015, the search for megastructures captured public attention through the case of KIC 8462852, informally known as Tabby's star, after astronomer Tabitha Boyajian, who led the initial investigation. This otherwise ordinary F-type star, located approximately 1,400 light-years from Earth in the constellation Cygnus, displayed highly unusual brightness fluctuations unlike anything previously observed in stellar astronomy. Data from NASA's Kepler Space Telescope revealed that Tabby's star would occasionally dim by up to 22%, with irregular patterns that could not be easily explained by planetary transits, stellar activity, or other common phenomena. The depth, duration, and irregularity of these dimming events suggested something massive and possibly non-spherical was intermittently blocking the star's light. While most astronomers favored natural explanations such as circumstellar dust or disintegrating comets, some researchers noted that the observations were also consistent with the transit of artificial structures, such as a partial Dyson swarm under construction. This possibility, while considered unlikely compared to natural explanations, nonetheless brought the search for megastructures into mainstream scientific and public discourse. Subsequent observations of Tabby's star using infrared telescopes failed to detect the excess infrared emission expected from a Dyson structure, and further monitoring revealed additional dimming events with characteristics that increasingly pointed towards circumstellar dust as the most likely explanation. The case illustrates both the excitement and the methodological caution that characterize the search for megastructures, as well as the difficulty of conclusively identifying artificial structures from limited astronomical data. Despite these challenges, the search for megastructures has grown increasingly sophisticated in recent years, benefiting from new observational capabilities and analytical approaches. The field has expanded beyond the original concept of Dyson spheres to consider a wider range of potential engineering signatures that might be detected through various observational methods. One promising avenue involves the use of large-scale astronomical surveys that repeatedly measure the brightness of billions of stars over extended periods. Projects like the European Space Agency's Gaia mission and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time provide unprecedented monitoring of stellar variability across much of the visible sky. Unusual light curves, particularly those showing non-periodic dimming with distinctive geometric patterns, might indicate transiting megastructures. Spectroscopic surveys also offer valuable data for megastructure searches. The chemical composition of a star system might be altered by large-scale mining operations or industrial activity, potentially creating spectral signatures distinguishable from purely natural processes. Advanced civilization might also produce industrial pollution or waste heat observable in the infrared or other wavelengths. Anomalous transit spectroscopy represents another detection method, where the spectrum of starlight changes as it passes through or reflects off orbiting structures. Unlike natural objects like planets or dust clouds, engineered structures might create distinctive spectral features based on artificial materials or precise geometric arrangements. The search extends beyond individual stars to encompass entire galaxies or galaxy clusters. Theoretical work by physicist Carl Sagan and others has suggested that sufficiently advanced civilizations might re-engineer astronomical objects on galactic scales, creating detectable anomalies in galactic light distribution, stellar populations, or energy emissions. Recent studies have examined galaxies with unusual infrared profiles that might indicate widespread stellar engineering, though alternative natural explanations remain viable for the observed anomalies. One particularly intriguing approach searches for technological waste heat across cosmic scales. A 2015 study analyzed data from the Wide-Field Infrared Survey Explorer to place constraints on the prevalence of galaxy-spanning civilizations. The research examined 50 million galaxies, seeking those with unusually high mid-infrared emission that might indicate widespread use of stellar energy. Finding no clear examples of galaxies with the expected Techno signature, the study concluded that Kardashev Type 3 civilizations, those harnessing the energy of entire galaxies, must be rare or non-existent in the observable universe, with an upper limit of one such civilization per 10 million galaxies. This astronomical search for waste heat represents perhaps the furthest reaching SETI effort to date, potentially capable of detecting technological activity across billions of light years. The approach demonstrates how the search for Techno signatures has expanded from its initial focus on nearby stars to encompass progressively larger cosmic scales, reflecting both growing observational capabilities and evolving conceptions of what advanced technology might entail. The theoretical frameworks supporting megastructure searches have also grown more sophisticated. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, categorizes civilizations based on their energy usage. Type 1 harnesses the energy available on their planet. Type 2 controls the energy of their star, and Type 3 utilizes the energy of their entire galaxy. This classification system, while simplified, provides a useful framework for considering the observational signatures of civilizations at different stages of development. More recent theoretical work has expanded on this foundation to consider the specific engineering requirements, physical limitations, and potential motivations for constructing various megastructures. These analyses draw on fields ranging from materials science and structural engineering to thermodynamics and information theory, bringing interdisciplinary rigor to what was once primarily speculative thinking. They also consider the evolutionary trajectory of technological civilizations, asking questions about the long-term fate of intelligence and its potential expression through cosmic engineering. Would advanced civilizations prioritize expanded habitation space, computational resources, energy collection, or purposes we cannot yet conceive? Different priorities would lead to different types of megastructures and thus different observational signatures. Some theorists have proposed that truly advanced civilizations might be driven by fundamental physical and computational limits to deploy their technology at astronomical scales. Information theory suggests that computations become more efficient at lower temperatures due to thermodynamic principles. This might motivate advanced artificial intelligence or uploaded consciousness to move progressively outward from stars, perhaps eventually preferring the cold outer reaches of stellar systems, or even the cold background of intergalactic space for maximum computational efficiency. Such possibilities expand our search beyond the traditional Dyson sphere concept to consider a wider range of potential technosignatures, from precisely engineered asteroid patterns to artificial modifications of planetary system architecture. They also suggest that we should look not just for energy-maximizing structures, but for entropy-optimizing ones, designed to extract maximum computational value, rather than raw power from available resources. Despite the theoretical sophistication and expanding observational capabilities, the search for megastructures confronts several persistent challenges. Perhaps the most fundamental is the ambiguity of potential detections. Astronomical observations typically provide limited information about distant objects, making it difficult to distinguish between rare natural phenomena and artificial constructions. As astronomer Jason Wright has noted, the history of astronomy includes many objects initially suspected to be artificial that were eventually explained through natural processes. This challenge is compounded by our limited understanding of stellar evolution and behavior. Stars exhibit a wide range of variability patterns, many of which remain incompletely understood. As our knowledge of natural stellar phenomena expands, some candidates for artificial megastructures may find natural explanations, while improved understanding may also help identify truly anomalous objects that warrant closer scrutiny. Another significant challenge involves the timescales of megastructure construction and observation. If advanced civilizations build Dyson spheres or similar structures incrementally over thousands or millions of years, we might observe systems in various stages of this process. However, distinguishing between a partial Dyson swarm under construction and natural phenomena like asteroid belts or protoplanetary disks would require detailed observations beyond current capabilities for most distant stars. The search for megastructures also confronts the question of motivation and universality. While energy capture represents a seemingly logical goal for technological advancement, we cannot know whether all or even most advanced civilizations would pursue this path. Cultural values, alternative technologies, or entirely different evolutionary trajectories might lead intelligent beings to expressions of technology that differ fundamentally from our expectations. Despite these challenges, the search for megastructures represents a uniquely promising approach within the broader field of techno-signature research. Unlike signals that must be deliberately transmitted or that might cease if a civilization falls silent, physical structures would likely persist for cosmological timescales, remaining detectable long after their creators had vanished. This permanence creates an asymmetry in detection probability compared to communication-based techno-signatures, potentially favoring the discovery of ancient megastructures rather than active communications. Furthermore, large-scale engineering projects would likely be visible from many vantage points across great distances, unlike directed communication that might only be detectable along specific sight lines. This omnidirectional visibility significantly increases the volume of space within which such techno-signatures could be detected. The search for megastructures connects with broader questions about the future of our own civilization and its potential cosmic impact. As humanity's technological capabilities grow, we ourselves might someday contemplate astronomical scale engineering, whether for energy collection, habitat creation, or purposes we have not yet imagined. By considering how we might detect such projects around other stars, we are in some sense looking into a possible future mirror, glimpsing what our own techno-signatures might someday become. This perspective creates a unique temporal symmetry in the search for megastructures. We seek evidence of technologies that might lie both in our future and in our past, artifacts created by civilizations that might be thousands or millions of years more advanced than our own, yet whose early development might have paralleled our current trajectory. In this sense, the search for megastructures is not merely a quest to find others, but an exploration of potential cosmic futures, an attempt to understand the long-term expression of technological intelligence within the universe. Whether we eventually detect clear evidence of artificial structures around distant stars, or continue to find only ambiguous candidates and natural explanations, the search itself expands our conception of what is possible and what might someday be. As new observatories come online and techniques for analyzing astronomical data grow more sophisticated, the search for megastructures continues to evolve. Each unusual light curve, each anomalous infrared source, each unexplained spectral feature represents a potential glimpse of cosmic engineering. And while most will likely find natural explanations, the possibility remains that somewhere among the billions of stars we observe, we might detect the unmistakable geometric precision or thermodynamic impossibility that would announce the presence of minds that have shaped the very heavens to their purpose. When we gaze at the night sky, most of the light reaching our eyes has traveled vast distances from distant stars. But among those countless points of light are much fainter objects, planets orbiting alien suns. In recent decades, astronomers have developed remarkable tools to detect and study these distant worlds, not just confirming their existence, but beginning to analyze their atmospheric composition through the subtle spectral fingerprints they imprint on starlight. As our ability to characterize exoplanet atmospheres grows more sophisticated, researchers have realized these same techniques might reveal not just the chemistry of alien biospheres, but the technological activities of advanced civilizations. This emerging field of atmospheric technosignatures represents one of the most promising new frontiers in the search for extraterrestrial intelligence. Unlike radio signals that must be deliberately transmitted or megastructures that require astronomical scale engineering, atmospheric technosignatures could result from industrial activities similar to our own, potentially detectable at earlier stages of technological development. The core concept is straightforward. Human civilization has profoundly altered Earth's atmosphere through industrial processes, agriculture, and energy production. These activities have introduced compounds that would not exist in significant quantities without technological intervention, from chlorofluorocarbons and sulfur hexafluoride to elevated concentrations of carbon dioxide and methane. If alien civilizations follow similar technological development paths, their planetary atmospheres might likewise bear the chemical signatures of their industrial activities. The idea that Earth's anthropogenic atmospheric changes might serve as a model for detecting technology on other worlds emerged in the scientific literature in the early 2000s. In 2005, astrobiologist David Grinspoon suggested that human-generated chlorofluorocarbons, artificial compounds used in refrigeration and manufacturing, could serve as unambiguous technosignatures if detected in exoplanet atmospheres, as these complex molecules have no known natural production pathways. This concept was expanded by astronomer Sarah Seeger and colleagues, who noted that while most discussions of atmospheric biosignatures focus on gases produced by life itself, such as oxygen from photosynthesis, technological activity creates its own distinctive suite of compounds. These technosignature gases might provide a more definitive indication of intelligence than biological signatures alone, as they would reveal not just the presence of life, but its technological modification of the environment. Unlike traditional SETI approaches focused on deliberate communications, atmospheric technosignatures would be unintentional byproducts of industrial civilization. Their detection would not require aliens to be actively attempting communication, merely that they had developed technology similar enough to our own to produce recognizable atmospheric alterations. This passivity potentially expands the window for detection, as the signatures could persist even if a civilization were unaware of our observations or uninterested in interstellar contact. What specific compounds might serve as compelling atmospheric technosignatures? Several categories have emerged as particularly promising candidates. Chlorofluorocarbons, or CFCs, represent perhaps the clearest example of a purely artificial compound. These synthetic chemicals, consisting of carbon atoms bonded to chlorine and fluorine, were widely used as refrigerants, propellants, and solvents during the 20th century before their ozone-depleting properties led to international restrictions on their production. CFCs have no known natural sources, requiring industrial chemistry for their creation. Their molecular structure is sufficiently complex that spontaneous formation through non-biological processes is extremely unlikely. Further adding to their value as technosignatures, many CFCs have atmospheric lifetimes ranging from decades to centuries, allowing them to accumulate to potentially detectable levels even if their production is limited to a relatively brief period in a civilization's development. Their distinctive absorption, features in the infrared portion of the spectrum, could theoretically be identified through transit spectroscopy of exoplanets, where starlight passing through the planetary atmosphere reveals the chemical fingerprints of its composition. Nitrogen dioxide represents another promising technosignature candidate, This reddish-brown gas forms primarily through high-temperature combustion processes, particularly from vehicles, power plants, and industrial facilities. While some natural sources exist, such as lightning and wildfires, the elevated concentrations resulting from industrial activity create a potential signal that might be detectable on other worlds. The gas has a relatively short atmospheric lifetime, which means its presence would indicate ongoing technological activity rather than historical production. Perhaps most intriguingly, nitrogen dioxide contributes to the formation of photochemical smog, which creates distinctive spectral features and could potentially be visible as a global haze layer. The characteristic coloration of nitrogen dioxide might even create detectable changes to a planet's overall appearance, particularly in how its reflectivity varies with wavelength. This raises the possibility that some atmospheric technosignatures might be detectable not just through spectroscopy, but through direct imaging of exoplanets, a capability expected to advance significantly with next-generation telescopes. Sulfur hexafluoride provides another example of an artificial compound with potential as a technosignature. This extremely potent greenhouse gas, used primarily as an electrical insulator in high-voltage equipment, has an atmospheric lifetime measured in thousands of years and no known natural sources. Its molecular structure makes it an excellent absorber of infrared radiation, creating distinctive spectral features potentially identifiable in exoplanet observations. Beyond these specific compounds, broader atmospheric alterations might also serve as technosignatures. The most obvious example is the enhanced greenhouse effect resulting from carbon dioxide emissions. While carbon dioxide itself is naturally occurring, technological civilizations might significantly increase its atmospheric concentration through fossil fuel combustion or similar activities, potentially creating detectable changes in a planet's energy balance and temperature. A particularly interesting case involves combinations of gases that would not naturally coexist in chemical equilibrium. For example, the simultaneous presence of significant quantities of both methane and oxygen in Earth's atmosphere represents a chemical disequilibrium maintained by biological activity, as these compounds would otherwise react to form carbon dioxide and water. Similar disequilibrium states maintained by technological activity might provide distinctive atmospheric signatures unique to industrial civilizations. For instance, the combination of a highly industrialized atmosphere with compounds indicating extensive factory farming of animals might represent a technosignature specific to a certain developmental phase, similar to Earth's current condition. Such complex atmospheric combinations could potentially provide more definitive evidence than any single compound alone. The field of atmospheric technosignatures gained significant momentum with the 2018 publication of a major review paper in the Astronomical Journal by Jacob Hack-Misra and colleagues. This comprehensive analysis systematically evaluated various industrial and technological gases as potential technosignatures, considering their spectral features, atmospheric lifetimes, and the minimum quantities that might be detectable with current or planned observatories. The study highlighted both the promise and challenges of this approach. While many artificial compounds create distinctive spectral signatures that could theoretically be identified in exoplanet atmospheres, their detection would require both significant atmospheric concentrations and observational capabilities beyond what is currently available for most exoplanets. Nevertheless, the authors concluded that atmospheric technosignatures represent a viable and potentially rewarding avenue for SETI research as observational technologies continue to advance. Current and planned astronomical facilities offer increasingly powerful capabilities for characterizing exoplanet atmospheres. The Hubble Space Telescope has already demonstrated the ability to detect certain atmospheric components around planets orbiting nearby stars, though primarily limited to large gas giants, rather than potentially habitable worlds. The recent launch and deployment of the James Webb Space Telescope marks a revolutionary advance in this field. With its large mirror and sophisticated spectrographs operating in the infrared portion of the spectrum, Webb can analyze the atmospheric composition of exoplanets with unprecedented sensitivity. This includes the potential to study smaller, rocky worlds more similar to Earth, particularly those orbiting the cooler red dwarf stars that comprise the most common stellar type in our galaxy. While detecting artificial compounds like CFCs would still be challenging even for Webb, the telescope's capabilities bring us significantly closer to the detection threshold for atmospheric technosignatures. Certain compounds, if present in sufficient quantities, might be identifiable during transit observations when planets pass in front of their host stars from our perspective, allowing starlight to filter through their atmospheres. Looking further ahead, proposed facilities like the Habitable Exoplanet Observatory or Large UV Optical Infrared Surveyor could potentially provide even greater sensitivity for atmospheric characterization. These space-based observatories, if approved and constructed, would offer the ability to study Earth-sized planets around Sun, like stars in detail, potentially bringing atmospheric technosignatures fully within observational reach. Ground-based facilities are also contributing to this endeavor. Extremely large telescopes currently under construction in Chile and Hawaii, with primary mirrors spanning 30 meters or more, will provide unprecedented light-gathering capability. When coupled with advanced adaptive optic systems to compensate for atmospheric distortion and sophisticated spectrographs to analyze the collected light, these telescopes will significantly advance our ability to study exoplanet atmospheres from Earth's surface. The scientific search for atmospheric technosignatures remains in its early stages, with much of the work thus far focused on theoretical calculations, modeling, and preparation for future observations rather than actual detection attempts. Researchers have developed increasingly sophisticated models of how various artificial compounds would manifest in exoplanet spectra, the quantities that would be required for detection, and the observational approaches most likely to succeed. These studies highlight several key challenges. Perhaps the most significant limitation is simply the difficulty of detecting any atmospheric components of Earth-sized exoplanets, let alone specific trace gases that might indicate technology. The planets themselves are extraordinarily faint compared to their host stars, typically billions of times dimmer, and their atmospheres represent just a tiny fraction of that already minimal signal. Successfully extracting atmospheric spectra requires either observing planets during transit, when they pass directly between their star and Earth, or through direct imaging techniques that must somehow suppress the overwhelming glare of the host star. Both approaches present enormous technical challenges that astronomers are only beginning to overcome. Even with ideal observing conditions and next-generation telescopes, many potential technosignature gases would need to be present in concentrations significantly higher than those found in Earth's atmosphere to be detectable across interstellar distances. This raises questions about the likely atmospheric impact of alien industrial activities, which might follow very different developmental trajectories than our own. Would extraterrestrial civilizations necessarily produce the same atmospheric pollutants as humans? Might they develop cleaner technologies earlier in their industrial evolution? Or conversely, might they engage in even more intensive atmospheric modification? These uncertainties complicate the search, but also expand the range of possibilities worth investigating. The challenge extends to distinguishing technosignatures from potential false positives. Some compounds that might seem indicative of technology could potentially have natural origins under certain planetary conditions. For instance, recent research has explored whether certain chlorine-bearing molecules previously considered potential technosignatures might actually form naturally on some types of exoplanets. Conversely, certain natural atmospheric states might mimic expected technosignatures. Planets experiencing runaway greenhouse effects through purely natural processes might display spectral signatures similar to those expected from industrial carbon dioxide emissions. Careful analysis of the overall planetary context and the specific combination of atmospheric constituents would be necessary to distinguish between technological and natural causes for observed atmospheric compositions. The time dimension adds another layer of complexity. Earth's atmosphere has changed dramatically over our planet's lifetime, with the rise of oxygen representing perhaps the most significant shift approximately 2.5 billion years ago as a result of biological activity. More recently, human technology has created its own atmospheric alterations on timescales of mere centuries or even decades. This temporal variability means that the atmospheric technosignatures of a given planet might appear dramatically different depending on when we happen to observe it. A civilization just entering its industrial phase, one at the height of fossil fuel use, and one that has transitioned to sustainable energy systems, would each create distinctive atmospheric signatures. The brevity of certain developmental phases, such as peak hydrocarbon combustion, might mean that some of the most obvious technosignatures exist for only a small fraction of a planet's history. Despite these challenges, atmospheric technosignatures offer several compelling advantages compared to other SETI approaches. Unlike intentional signals that require aliens to be deliberately communicating, or megastructures that would represent extraordinarily advanced engineering capabilities, atmospheric changes begin early in a civilization's technological development. This broader window of opportunity could significantly increase the likelihood of detection, particularly if technological civilizations commonly emerge but only rarely achieve the capability or motivation for interstellar communication. Additionally, the methods and instruments required to search for atmospheric technosignatures largely overlap with those already being developed for general exoplanet characterization and the search for biosignatures. This creates opportunities for SETI to benefit from major astronomical investments without requiring dedicated facilities, potentially allowing the search for technosignatures to proceed as a complementary objective alongside more conventional exoplanet science. The field also benefits from its grounding in known technology and atmospheric chemistry. Unlike searches for alien engineering beyond our technological comprehension, atmospheric technosignatures can be based on actual compounds already produced by human civilization, providing concrete targets with well-understood spectral properties. This empirical foundation helps move the search from speculation towards specific, testable predictions. Perhaps most significantly, the search for atmospheric technosignatures creates a natural bridge between traditional SETI and mainstream astronomy, particularly the rapidly growing field of exoplanet science. By focusing on observable planetary properties rather than speculative communications, this approach frames the search for intelligence as a logical extension of our broader investigation of cosmic habitability and planetary evolution. This integration with exoplanet science has catalyzed important cross-disciplinary collaborations, bringing together specialists in fields ranging from atmospheric chemistry and planetary science to spectroscopy and telescope instrumentation. Such collaborations have been further strengthened by NASA's increasing recognition of technosignatures as a legitimate research area, including dedicated workshops and funding opportunities that were largely absent during earlier decades of SETI research. As we look toward future observational capabilities, the search for atmospheric technosignatures will likely focus initially on planets orbiting the nearest stars, particularly those within approximately 50 light-years, where spectroscopic observations can achieve the highest sensitivity. M-dwarf stars may offer particularly promising targets due to their abundance and the larger atmospheric signal provided by planets transiting these smaller stellar hosts. The TRAPPIST-1 system, a nearby red dwarf with 7 Earth-sized planets, 3 of which lie within the traditional habitable zone, exemplifies the type of system that might eventually allow detailed atmospheric characterization. Similar systems discovered by NASA's Transiting Exoplanet Survey satellite and other planet-hunting missions will expand the list of promising targets for atmospheric investigation. Beyond these nearby systems, statistical approaches might eventually allow the identification of broader patterns across larger planetary samples, even if individual atmospheric components cannot be precisely determined. For instance, systematic differences in the atmospheric properties of planets at similar cosmic evolution stages might suggest the influence of technology on a subset of worlds. Given humanity's own impact on Earth's atmosphere and the existential questions raised by climate change, the search for atmospheric technosignatures carries particular resonance. As we study the potential atmospheric markers of alien technology, we inevitably reflect on our own planetary modifications and their long-term implications. This creates a unique connection between SETI research and terrestrial environmental concerns, each informing our understanding of the other. If we eventually detect signs of industrial pollution in the atmosphere of a distant world, what might that tell us about the sustainability of technological civilization? Would the presence of greenhouse gases similar to our own suggest that other species face climate challenges similar to humanity's current predicament? Or might we instead discover evidence of civilizations that have passed through such crises and achieved more sustainable relationships with their planetary systems? These questions highlight how the search for atmospheric technosignatures extends beyond the simple detection of intelligence to touch on deeper questions about the cosmic prevalence and longevity of technological civilization. Each exoplanet atmosphere we analyze becomes not just a potential indicator of alien presence, but a possible window into alternative technological trajectories and their planetary consequences. As we develop increasingly powerful tools to study worlds beyond our solar system, the thin gaseous envelopes surrounding distant planets may yet reveal the most profound evidence that we are not alone, not through deliberate messages beamed across the cosmos, but through the subtle chemical signatures of another species reshaping their world through technology, just as we have reshaped our own. The search for extraterrestrial intelligence has traditionally focused on electromagnetic radiation, those familiar waves of energy that include visible light, radio waves, and infrared signals. This focus makes practical sense, as electromagnetic waves propagate efficiently through the vacuum of space and form the foundation of our own communication technologies. Yet, as our scientific understanding expands and our technological capabilities advance, researchers have begun to consider a broader range of potential technosignatures that lie beyond the electromagnetic spectrum, from elementary particles to distortions in space-time itself. These alternative channels for detecting advanced civilizations offer both promise and challenge. Some might allow communication or detection across distances or timescales inaccessible to conventional approaches. Others might provide evidence of exotic technologies far beyond our current capabilities, but potentially within reach of sufficiently advanced species. While more speculative than traditional SETI methods, the search for non-electromagnetic technosignatures expands our conception of how intelligence might manifest itself across cosmic distances and timescales. Among the most promising non-electromagnetic particles for potential communication or detection are neutrinos, ghostly subatomic particles produced abundantly in stars and certain nuclear reactions. Neutrinos interact so weakly with matter that they can pass through entire planets virtually unimpeded, with trillions streaming through your body every second without effect. This near transparency to matter allows neutrinos to travel unobstructed across vast cosmic distances without absorption or scattering. Natural neutrino sources include nuclear fusion within stars, supernova explosions, and various high-energy astrophysical processes. However, artificial neutrino beams can also be generated through particle accelerators and certain types of nuclear reactors. While human neutrino generation capabilities remain relatively modest, a significantly more advanced civilization might potentially create directional neutrino beams of sufficient intensity to serve as communication channels across interstellar distances. The advantages of neutrino communication would be significant for certain applications. Unlike electromagnetic signals, neutrinos would not be blocked by intervening matter such as molecular clouds or the centers of planets or stars. They would arrive almost perfectly unaltered from their source, even across intergalactic distances. A neutrino signal could potentially reach recipients who were otherwise inaccessible via electromagnetic transmission, or might serve as an uninterruptible emergency channel resistant to cosmic interference. However, the same properties that allow neutrinos to penetrate matter so effectively also make them exceptionally difficult to detect. Current neutrino observatories consist of enormous volumes of material, often thousands of tons of water or ice located deep underground to shield from cosmic rays, monitored for the extremely rare interactions between neutrinos and atoms. Even with these massive detectors, only a tiny fraction of passing neutrinos are observed. This detection challenge suggests that any neutrino-based technosignature would likely require either truly extraordinary transmission power or detection capabilities far beyond our current technology. Nevertheless, several researchers have proposed search strategies for artificial neutrino sources that might be distinguishable from natural background emissions. One approach would look for neutrinos with energy levels or directional characteristics inconsistent with known natural production mechanisms. Another would search for temporal patterns in neutrino arrivals, suggesting encoded information, similar to how radio SETI searches for structured signals rather than random emissions. While current detectors were not designed with SETI applications in mind, data from facilities such as IceCube at the South Pole, Super Kamiokande in Japan, and Antares in the Mediterranean Sea could potentially be analyzed for anomalous signals that might have artificial origins. Beyond neutrinos, gravitational waves represent another non-electromagnetic phenomenon with potential SETI applications. First predicted by Einstein's general theory of relativity and directly detected for the first time in 2015, gravitational waves are ripples in the fabric of spacetime itself, generated by accelerating massive objects such as colliding black holes or neutron stars. Natural sources of gravitational waves typically involve extraordinary cosmic events releasing enormous energies, such as binary black hole mergers, converting several solar masses directly into gravitational wave energy within fractions of a second. However, the theoretical possibility exists that sufficiently advanced civilizations might artificially generate or manipulate gravitational waves for communication or other technological purposes. The advantages of gravitational wave communication would include many of the same benefits as neutrinos, propagating virtually unimpeded across cosmic distances. Additionally, gravitational waves are inherently directional, carrying information about their source orientation that might be useful for communication purposes. As with neutrinos, the primary challenge involves the immense difficulty of both generation and detection. Currently, humanity can only detect gravitational waves from the most energetic events in the universe, and we have no practical means of generating detectable waves ourselves. Any artificial gravitational wave technosignature would require technology so far beyond our current capabilities that specific detection strategies remain largely speculative. Nevertheless, as our gravitational wave observatories become more sensitive and numerous, the possibility emerges of searching for anomalous signals that don't match expected natural sources. Particularly interesting would be gravitational wave patterns, with features suggesting information encoding, such as precisely modulated frequencies or complex temporal structures, inconsistent with natural generation mechanisms. Theoretical work has also explored gravitational wave signatures that might result from extremely advanced propulsion systems, such as massive objects accelerated to relativistic speeds, or artificial manipulation of black holes for energy extraction. While detecting such signatures remains beyond current capabilities, future gravitational wave observatories operating across wider frequency ranges with greater sensitivity might eventually enable searches for such exotic technosignatures. Another fascinating category of potential non-electromagnetic technosignatures involves quantum mechanical phenomena. Quantum entanglement, described by Einstein as spooky action at a distance, creates correlations between particles that persist, regardless of the separation between them. This property forms the basis for quantum communications research on Earth, with potential applications for secure information transmission. Some theorists have suggested that sufficiently advanced civilizations might utilize entangled particles for interstellar communication, potentially enabling instantaneous information exchange across arbitrary distances. While such communication would appear to violate the cosmic speed limit established by the speed of light, careful analysis indicates that no actual faster-than-light information transfer occurs, preserving consistency with relativity. The practical challenges of maintaining quantum entanglement across stellar distances appear formidable, requiring extraordinary technological capabilities beyond our current understanding. Nevertheless, Certain quantum mechanical signatures, potentially detectable through specialized instruments, might conceivably reveal evidence of advanced quantum technologies deployed by other civilizations. The list of potential non-electromagnetic techno-signatures extends further into increasingly speculative territory. Cosmic rays, high-energy particles originating from beyond our solar system, could potentially be artificially generated or modulated by sufficiently advanced technology. Certain patterns in cosmic ray arrivals, particularly those exhibiting non-random distributions inconsistent with known astrophysical processes, might warrant investigation as potential techno-signatures. Multiple research groups have proposed searching for evidence of self-replicating probes or advanced artificial intelligence exploring the galaxy. Such entities, sometimes called von Neumann probes, after mathematician John von Neumann, who described their theoretical foundation, might be programmed to travel between star systems, utilizing local resources to create copies of themselves that would continue the exploration process exponentially. If such probes exist within our solar system, they might leave detectable signatures through their resource utilization, energy emissions, or direct observation. Various searches have examined lunar and solar system imagery for anomalous objects, analyzed orbital patterns for artificial satellites not of human origin, and proposed methods for detecting the thermal or electromagnetic emissions that might accompany extraterrestrial technology operating within our cosmic neighborhood. A particularly intriguing possibility involves artifacts deliberately placed to be discovered, sometimes called calling cards or cosmic archaeological artifacts. Unlike active signals requiring continuous energy expenditure, passive artifacts could persist for geological or even astronomical timescales, waiting to be found by emerging technological species. Such objects might be positioned in prominent or easily accessible locations, such as stable Lagrange points within planetary systems, or might incorporate distinctive features designed to be recognizable as artificial rather than natural formations. Several researchers have proposed systematic searches for such artifacts within our solar system, including careful examination of near-Earth asteroids, lunar and planetary surfaces, and dynamically stable regions where objects could remain undisturbed for billions of years. The 5 Lagrange points of the Earth-Moon system, where gravitational forces create stable or semi-stable orbits, represent particularly promising locations, as they would be relatively accessible to any emerging technological civilization in the system. The search for techno-signatures extends even to the realm of nuclear physics and fundamental particles. Advanced civilizations might potentially create or manipulate isotopes or elementary particles in ways that leave distinctive signatures. Unusual isotope ratios in certain locations, or particles with properties that appear engineered rather than natural, could conceivably indicate technological intervention. One specific proposal involves searching for evidence of artificial nuclear isomers, atomic nuclei containing excess energy in metastable states. These isomers could theoretically store substantial energy for extended periods before releasing it on command, potentially serving as high-density energy storage for advanced applications. Natural processes rarely produce significant concentrations of nuclear isomers, so their detection in abundance would raise questions about possible artificial origin. The concept of cosmic engineering extends these ideas to their logical conclusion, suggesting that sufficiently advanced civilizations might manipulate astronomical objects or even physical laws themselves. Theoretical physicist Freeman Dyson, whose work on megastructures we explored earlier, also proposed searching for evidence of technological tinkering with the fundamental constants of the universe, suggesting that advanced intelligence might eventually gain the capability to engineer physics itself. While such proposals venture far beyond current human technological capabilities, they illustrate an important principle in the search for techno-signatures: the need to consider possibilities beyond our immediate technological horizon. After all, human civilization has advanced from primitive radio to quantum computing in barely a century, an infinitesimal period in cosmic terms. A civilization thousands or millions of years more advanced might employ technologies that would be indistinguishable from magic or fantasy to our current understanding. This reasoning leads to perhaps the most exotic category of potential techno-signatures, those involving hypothetical physics beyond our current scientific paradigm. While speculative by definition, the history of science suggests that our understanding of physical reality continues to evolve, often in revolutionary ways. Future discoveries might reveal new particles, forces, or dimensions that could be utilized by advanced technological civilizations in ways currently unimaginable. Some theoretical physicists have suggested that certain astronomical anomalies or unexplained observations might potentially represent evidence of such exotic technologies. For instance, unexplained correlations in cosmic background radiation, unexpected particle behaviors, or discrepancies in fundamental physical constants across cosmic distances might conceivably result from technological intervention rather than natural processes. The challenge, of course, lies in distinguishing genuinely artificial signatures from either known natural phenomena or gaps in our current scientific understanding. Throughout the history of astronomy, numerous observations initially considered anomalous have eventually found natural explanations as our knowledge advanced. This pattern reminds us that extraordinary claims require extraordinary evidence, particularly when considering potential techno-signatures far beyond our current technological paradigm. The search for non-electromagnetic and exotic techno-signatures also confronts a fundamental limitation: our inability to fully anticipate the technological trajectory of advanced civilizations. We necessarily search for technologies we can imagine and potentially detect, but these may represent only a small subset of what actually exists. Just as radio technology would have been inconceivable to ancient civilizations, advanced extraterrestrial technology might operate on principles entirely outside our current scientific framework. This limitation has led some researchers to propose more agnostic approaches, focusing on identifying anomalies or observations that cannot be explained through known natural processes, rather than searching for specific, anticipated techno-signatures. Such anomaly-based SETI would cast a wider net, potentially capturing evidence of technologies we cannot yet conceptualize, though at the cost of generating more false positives, requiring careful investigation. Despite these challenges, the exploration of non-electromagnetic and exotic techno-signatures has garnered increasing scientific attention in recent years. Several factors have contributed to this expansion beyond traditional SETI approaches, including the continued absence of clear detections from conventional searches, the development of new observational capabilities across multiple fields, and evolving theoretical understanding of what advanced technology might entail. The integration of SETI considerations into broader astronomical and physical research has been particularly significant. Rather than requiring dedicated facilities or programs, many searches for exotic techno-signatures can be conducted through analysis of data already being collected for conventional scientific purposes. This creates opportunities for SETI to advance alongside mainstream science, benefiting from investments in areas ranging from particle physics to cosmology without requiring separate justification. The rise of computational astronomy and big data analytics has further enabled this integration, allowing researchers to search vast data sets for patterns or anomalies that might indicate technological origin. Machine learning algorithms in particular offer promising tools for identifying signals that might elude conventional analysis methods, potentially revealing techno-signatures hidden within existing astronomical observations. The search for artifacts within our own solar system has gained particular momentum in recent years, partly due to the dramatic increase in our observational coverage of nearby space. Numerous missions have mapped the lunar surface at unprecedented resolution. Rovers have explored Mars with increasingly sophisticated instruments, and probes have visited every major planet and many smaller bodies throughout the solar system. This expanded observational capability has coincided with growing scientific interest in the possibility of interstellar objects passing through our system. The 2017 discovery of Oumuamua, the first confirmed interstellar object detected within our solar system, demonstrated that material regularly travels between star systems. While Oumuamua appears natural despite some unusual characteristics, its discovery validated the concept that interstellar objects, whether natural or artificial, might occasionally pass close enough for detailed study. This realization has stimulated interest in developing capabilities to rapidly detect and potentially intercept future interstellar visitors, creating opportunities for technosignature research as a component of broader scientific investigation. The Galileo project, led by Harvard astronomer Avi Loeb, explicitly incorporates the search for potential extraterrestrial artifacts among its research objectives, alongside more conventional studies of interstellar objects and atmospheric anomalies. Astronomical surveys designed primarily for planetary defense, mapping potentially hazardous asteroids that might threaten Earth, simultaneously create datasets that can be analyzed for objects with unusual trajectories or other characteristics, potentially indicating artificial origin. As these surveys grow more comprehensive and their data more accessible, the opportunity for artifact searches expands without requiring dedicated observational resources. The search for non-electromagnetic technosignatures also benefits from its inherent multidisciplinary nature, bringing together specialists from fields rarely connected in traditional research structures. Archaeologists experienced in identifying ancient human artifacts contribute methodological insights for recognizing technological signatures across vast timescales. Nuclear physicists provide expertise on potential isotopic or particle-based technosignatures. Computer scientists develop algorithms capable of identifying subtle patterns within massive datasets. This cross-disciplinary collaboration generates novel approaches and perspectives that might not emerge within more narrowly defined research communities. The resulting intellectual diversity strengthens the overall search for technosignatures by expanding the range of phenomena considered and the analytical tools applied to their detection. The exploration of exotic technosignatures also performs a valuable function in stretching our conception of what advanced technology might entail and how it might manifest across cosmic scales. By considering possibilities beyond our immediate technological horizon, we expand our search parameters and reduce the risk of missing evidence due to overly restrictive assumptions about how intelligence might express itself in the universe. This conceptual expansion carries significance beyond SETI itself, influencing how we think about the long-term future of our own technological civilization. By contemplating the potential signatures of technologies centuries or millennia beyond our current capabilities, we engage in a form of long-term forecasting that informs our understanding of humanity's possible cosmic future. Whether we eventually detect non-electromagnetic technosignatures or continue to find only the silent beauty of natural cosmic processes, the search itself propels us toward a more complete understanding of both the universe and our place within it. Each new observational capability, each theoretical framework for identifying potential signatures of technology, expands the scope of our cosmic questioning. In this sense, the search for exotic technosignatures embodies the essence of the scientific enterprise itself, the systematic exploration of possibilities, the rigorous examination of evidence, and the continuous refinement of our understanding based on empirical observation. As we develop increasingly sophisticated methods for detecting potential signs of technology beyond our current capabilities, we participate in humanity's grand project of cosmic self-discovery, asking not just whether we are alone, but what we might someday become. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to extraterrestrial life. After discussing the vastness of the universe and the mathematical probability that intelligent life might be common, Fermi reportedly asked a simple but profound question: where is everybody? This casual inquiry during a midday meal would eventually become known as the Fermi paradox, one of the most enduring and thought-provoking puzzles in our search for extraterrestrial intelligence. The paradox emerges from a seemingly irreconcilable contradiction. On one hand, When we consider the immensity of the cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, many with their own planetary systems, the probability arguments suggest intelligent life should be abundant. Add to this the age of the universe, approximately 13.8 billion years, providing ample time for civilizations to emerge and develop interstellar technology, and it seems the galaxy should be teeming with advanced species. On the other hand, we have detected no clear evidence of extraterrestrial intelligence. Our telescopes record no artificial radio signals from the stars. Our surveys find no unmistakable signs of cosmic engineering, and our solar system shows no definitive artifacts from visitors. This discrepancy between the expected prevalence of technological civilizations and the apparent silence of the cosmos constitutes the heart of Fermi's paradox. The tension grows sharper when we consider the timescales involved. Our Milky Way galaxy is approximately 13 billion years old, while Earth and our solar system formed less than 5 billion years ago. This means the galaxy existed for roughly 8 billion years before our planet even formed. If technological civilizations emerged on other worlds within that vast time span, even modest interstellar expansion at sublight speeds would have had sufficient time to reach across much or all of the galaxy before humans ever evolved. Simple calculations illustrate the point. Even if an expanding civilization could colonize new star systems at an average rate of just 1/10 the speed of light, including time for establishment and launching subsequent missions, they could theoretically spread across the entire Milky Way in less than 1 million years. This represents a mere instant in astronomical time, less than 1% of the galaxy's age. Yet we see no evidence of such widespread colonization or its technological footprint. This absence of detection, despite apparent probability, has spawned a rich literature of proposed resolutions, ranging from the mundane to the exotic, from the optimistic to the deeply unsettling. These potential explanations can be grouped into several broad categories, each carrying different implications for our search for technosignatures and our understanding of intelligence in the cosmos. Perhaps the most straightforward explanation suggests that technological civilizations are simply exceedingly rare. This rarity might result from one or more great filters in the pathway from simple chemistry to spacefaring intelligence, developmental hurdles so difficult that very few species ever overcome them. If correct, this would explain why we have yet to detect others, as the nearest technological civilization might be millions or billions of light years away, beyond our current detection capabilities. The Great Filter hypothesis prompts us to consider where in the developmental sequence from basic chemistry to interstellar civilization these prohibitive hurdles might occur. Are they behind us, suggesting humanity has already overcome the most difficult steps in cosmic evolution? Or do they lie ahead, implying that technological civilizations typically encounter existential challenges they rarely survive? The transition from simple prokaryotic cells to more complex eukaryotic cells took nearly 2 billion years on Earth, suggesting this step might be exceptionally difficult and rare. Similarly, the development of complex multicellular life required specific environmental conditions maintained over vast timescales. Intelligence itself, particularly the abstract reasoning and technological capability exhibited by humans, represents an evolutionary path taken by only one species among the millions that have existed on our planet. Alternative filters might include the development of science itself, which required specific cultural and cognitive conditions that might be uncommon among intelligent species. Or perhaps the greatest filters lie in our future, in challenges like nuclear weapons, climate change, artificial intelligence, or other technologies that create existential risks for their creators. If most technological civilizations destroy themselves shortly after developing advanced capabilities, their window for detection would be extremely brief on cosmic timescales. Astronomer Jason Wright has noted that the Great Filter explanation makes a testable prediction, that we should find that one or more steps in the pathway to intelligence are extraordinarily improbable. As our understanding of astrobiology, evolutionary biology, and planetary science advances, we may identify which specific transitions represent the most significant bottlenecks. A related explanation suggests that while intelligent life might be relatively common, technological civilizations capable of creating detectable techno-signatures might be exceptionally rare. Perhaps most intelligent species never develop advanced technology due to environmental limitations, biological constraints, or different evolutionary pathways that lead to intelligence without technological manipulation of the environment. Imagine aquatic species that evolve high intelligence but lack manipulative appendages or ready access to fire, limiting their technological development despite complex language and social structures. Or consider species that develop different forms of intelligence focused on immediate ecological awareness rather than abstract thinking and tool creation. Such civilizations might create rich cultures and profound philosophies without ever generating the kinds of techno-signatures our instruments could detect across interstellar distances. Another category of explanations focuses not on the rarity of technological civilizations, but on their behavior and detectability. Perhaps advanced species typically choose not to expand through the galaxy or make their presence known. They might exist in significant numbers, but remain undetectable due to technological or cultural choices. The zoo hypothesis proposes that Earth might be deliberately left undisturbed as a kind of cosmic nature preserve or sociological experiment. Advanced civilizations might follow something akin to Star Trek's Prime Directive, avoiding interference with emerging species until they reach a certain developmental threshold. If such a galactic quarantine exists, it would explain our apparent isolation, despite the potential abundance of advanced civilizations. A darker version of this non-interference hypothesis suggests security concerns might motivate cosmic silence. Advanced civilizations might recognize that broadcasting their location could attract unwanted attention from potentially hostile species or technologies. In a galaxy where resources remain finite despite their abundance, and where the vast distances between stars create significant communication delays, establishing first contact carries inherent risks that cautious species might choose to avoid. This perspective, sometimes called the dark forest theory, after Liu Cixin's science fiction novel of the same name, proposes that silence might be the optimal survival strategy in an uncertain cosmos. Like predators and prey in a dark forest, civilizations remain quiet and hidden, aware that revealing their location might attract those with unknown intentions and vastly different values. Under such conditions, Fermi's question, "Where is everybody?" would be answered simply, "Hiding as we should be." Technological evolution might also explain cosmic silence. Perhaps civilizations typically advance beyond technologies that produce easily detectable signatures. Our own civilization has already begun shifting from high-power, omnidirectional radio broadcasts toward more efficient, directed, and encrypted communications. This trend, if continued and common among technological species, would create a relatively brief window during which a civilization produces the kind of unintentional electromagnetic leakage that our SETI programs might detect. Following this trajectory further, advanced civilizations might eventually develop technologies so efficient that they produce minimal waste energy or material signatures detectable across interstellar distances. The science fiction author Arthur C. Clarke famously observed that any sufficiently advanced technology would be indistinguishable from magic, and truly advanced civilizations might employ methods beyond our current scientific understanding, operating in ways we cannot yet recognize. Several theorists have proposed that advanced intelligence might eventually transition toward increasingly efficient information processing, potentially even transferring consciousness into computational substrates. Such entities might minimize physical footprints while maximizing computational capacity, creating what some have termed matryoshka brains, layered computational structures surrounding stars to capture their energy for immense information processing capabilities. Such post-biological civilizations might focus inward rather than outward, exploring simulated universes or forms of consciousness beyond our comprehension rather than physical space. Their values, perceptions, and activities might diverge so significantly from biological experience that they would have little interest in the kinds of interstellar communication or exploration that would make them detectable to species like ourselves. The physicist John Smart has proposed a similar concept called the transcension hypothesis, suggesting that advanced civilizations might invariably turn inward, utilizing technologies that allow them to manipulate matter and energy at increasingly microscopic scales, eventually approaching quantum limits. This development pathway would lead toward increasing density of intelligence rather than expansive cosmic footprints, rendering them effectively invisible from our macro-scale perspective. A particularly sobering explanation for the Fermi paradox involves the potential instability of technological civilization itself. Perhaps intelligence capable of developing advanced technology typically creates the means of its own destruction before achieving sustainable interstellar presence. Nuclear weapons, climate change, artificial intelligence, nanotechnology, and bioengineered pathogens represent just a few of the existential risks that emerge alongside technological advancement. If most civilizations destroy themselves within centuries of developing radio technology, the odds of two technological species existing simultaneously within detection range of each other would be vanishingly small. The brief operational lifetime would explain cosmic silence without requiring technological civilizations to be intrinsically rare, merely short-lived in their detectable phase. This possibility carries profound implications for humanity's future. If the development of potentially destructive technologies typically outpaces the ethical, institutional, and security systems needed to manage them safely, we might be approaching our own great filter. Understanding whether this pattern holds across cosmic civilizations becomes not merely an abstract scientific question, but one with immediate relevance to our survival. Temporal factors might contribute to apparent cosmic silence, even if technological civilizations are relatively common. For us to detect another civilization through its techno signatures, both our technology and theirs must exist simultaneously, creating a temporal overlap that may be unlikely given cosmic timescales. Consider an analogy to human history on Earth. If an ancient Roman had somehow possessed a radio receiver, she would have detected no signals, despite the billions of humans who would eventually use radio technology. Similarly, if radio technology becomes obsolete in the next 1,000 years, replaced by currently unknown communication methods, a civilization examining Earth 10,000 years from now might detect no obvious techno signatures despite our current extensive radio activity. When extended to the billions of years of our galaxy's history, this temporal disjunction might make simultaneous detectable civilizations exceptionally rare, even if they are common in absolute numbers across cosmic time. We might be surrounded by the equivalent of cosmic archaeological sites, star systems where technological civilizations once flourished, but are now gone or transformed beyond recognition, leaving few obvious traces detectable with our current capabilities. Spatial factors compound this temporal challenge. Even if numerous technological civilizations exist simultaneously, the vast distances between stars mean that signals weaken with distance, eventually becoming indistinguishable from background noise. Our most powerful radio transmissions would be difficult to detect beyond a few hundred light years, using technology similar to our own, and this range encompasses only a tiny fraction of the galaxy's 100,000 light-year diameter. If technological civilizations are randomly distributed through the galaxy with even modest average separation, the probability of any falling within our current detection range becomes small. We might need significant advances in our search capabilities or extremely powerful transmissions specifically designed for interstellar communication to bridge these vast distances. The combination of spatial and temporal factors creates what some researchers call the brief window observation problem. For successful detection, Civilization A must create detectable techno-signatures that reach Civilization B during the specific window, when B has both the technology to detect them and is actively looking in the right direction with the right techniques. This conjunction of factors might be exceptionally rare, even if technological civilizations themselves are relatively common across cosmic history. Another intriguing possibility involves differing perceptions of reality and communication. Perhaps advanced civilizations communicate through channels or methods we cannot yet recognize or comprehend. Just as an ant colony cannot comprehend human communication through the internet, despite physically coexisting with it, we might be immersed in a galaxy filled with communications we lack the sensory or conceptual framework to perceive. This conceptual limitation might extend beyond communications to the nature of advanced intelligence itself. Our search necessarily focuses on techno-signatures we can imagine and detect based on our current scientific understanding. But this may represent only a narrow subset of how technology and intelligence might manifest across cosmic evolution. Some philosophers and complexity theorists have suggested that truly advanced intelligence might operate in ways fundamentally alien to human cognition and technological development. Rather than creating obvious artifice distinct from natural processes, advanced technological evolution might trend toward integration with and enhancement of natural systems, creating what some have termed technology indistinguishable from nature. Under such conditions, we might be searching for sharp distinctions between technological and natural processes, while the most advanced civilizations have transcended this dichotomy, creating technologies so integrated with natural systems that they appear as particularly elegant natural phenomena rather than obvious artifacts. The silence observed in our searches might also reflect fundamental physical or technological limitations that make interstellar communication or travel prohibitively difficult, regardless of a civilization's advancement. While no known physical law prevents interstellar communication, the practical challenges of transmitting detectable signals across light years, while overcoming cosmic background radiation and signal degradation, might prove more formidable than our optimistic projections suggest. Similarly, while interstellar travel appears theoretically possible within the laws of physics, the enormous energy requirements, technical challenges, and timescales involved might make it impractical for even highly advanced civilizations. If these barriers prove insurmountable or nearly so, the galaxy might contain numerous advanced but effectively isolated civilizations, each confined to their home systems or limited regions, without the means to create wider techno-signatures. The sociologist Stephen Webb has catalogued dozens of proposed solutions to the Fermi paradox, from the prosaic to the profound, in his book, If the Universe is Teeming with Aliens, Where is Everybody? His analysis highlights how this question intersects with nearly every scientific discipline, from astronomy and biology to sociology and philosophy, making it simultaneously one of the most interdisciplinary and most humbling questions in modern science. The diversity of potential explanations for cosmic silence reveals something important about our search for techno-signatures, that our expectations and search methodologies inevitably incorporate assumptions about the nature, behavior, and evolutionary trajectory of intelligence beyond Earth. These assumptions may limit our ability to recognize evidence that doesn't conform to our anticipated patterns, creating potential blind spots in our search strategies. To address this limitation, many SETI researchers have advocated for expanding beyond narrow conceptions of what techno-signatures might entail, developing more agnostic search methods focused on identifying anomalies or observations that cannot be explained through known natural processes. This approach might help us recognize potential evidence of intelligence operating outside our expected parameters. The Fermi paradox also influences how we interpret negative results in our searches. The absence of detected signals does not merely represent a lack of data, but carries information value itself. Each silent observation constrains the possible distribution and characteristics of technological civilizations, gradually narrowing the range of viable explanations for our apparent cosmic solitude. For instance, comprehensive surveys finding no evidence of Dyson spheres or similar stellar-scale engineering within thousands of nearby galaxies constrain the prevalence of energy-intensive civilizations operating at Kardashev Type 2 or 3 levels. Similarly, decades of radio silence across thousands of target stars limits the commonality of civilizations using high-power radio transmissions directed toward potentially habitable systems like our own. These constraints help refine our search strategies and theoretical understanding of how technological intelligence might manifest across cosmic scales. Rather than indicating failure, the accumulation of negative results progressively illuminates the parameter space within which solutions to the Fermi paradox must exist. The paradox also carries profound implications for humanity's potential cosmic future. If technological civilizations typically experience extinction or transcendence shortly after reaching our current developmental stage, this suggests we might be approaching a critical threshold in our evolution. Understanding whether silent skies indicate disaster or transformation becomes crucial to navigating our own technological adolescence. Conversely, if the explanation involves extreme rarity of intelligence capable of developing technology, this would suggest humanity occupies an exceptional position in cosmic evolution. Such cosmic uncommonness would arguably increase our ethical responsibility as potential caretakers of intelligence in our corner of the universe, placing special value on our long-term survival and development. In either case, the Fermi paradox transforms from abstract speculation to a question with direct relevance to humanity's relationship with technology, our understanding of existential risk, and our vision for our species' future. How we interpret cosmic silence influences how we approach innovations with both transformative potential and catastrophic risk, from artificial intelligence to biotechnology to nuclear energy. Perhaps most importantly, the paradox reminds us of the vast uncertainties in our understanding of cosmic evolution and the development of intelligence. Despite remarkable scientific progress in recent decades, fundamental questions about the frequency of life, the emergence of intelligence, and the typical trajectory of technological civilization remain largely unanswered. This humility before the unknown represents one of the paradox's most valuable contributions to our intellectual landscape. The search for techno-signatures continues against this background of profound questions and diverse hypotheses. Each telescope observation, each analysis of astronomical data, each new detection method developed contributes to our navigation of this mystery. While we have not resolved Fermi's question yet, our increasingly sophisticated search methodologies and theoretical frameworks bring us closer to understanding our place in the cosmic community of intelligence, whether that community proves crowded, sparse, or potentially unique. As we continue listening to the silence between stars, we participate in one of humanity's most profound inquiries. We ask not merely whether we are alone, but what our seeming solitude might mean for the nature of intelligence, the challenges of technology, and the future of consciousness in the cosmos. The apparent emptiness itself becomes data, the silence a signal, carrying information about the rarest and perhaps most precious phenomenon we have yet encountered in the universe: technological intelligence capable of wondering about its place among the stars. As we approach the midpoint of the 21st century, the search for techno-signatures stands at a pivotal moment in its evolution. After more than 60 years of formal scientific inquiry, no unambiguous evidence of extraterrestrial technology has been confirmed. Yet rather than diminishing in response to this silence, the field has expanded dramatically in scope, sophistication, and scientific legitimacy. New instruments, analytical techniques, interdisciplinary collaborations, and theoretical frameworks have transformed what was once considered a fringe scientific pursuit into a respected research enterprise engaging some of the world's leading scientific institutions. This transformation reflects both technological advancement and conceptual evolution. Our ability to detect potential techno-signatures has improved by orders of magnitude across multiple search modalities. Simultaneously, our understanding of what might constitute evidence of extraterrestrial technology has broadened far beyond radio signals to encompass dozens of potential techno signatures spanning the electromagnetic spectrum and beyond. This convergence of expanded capabilities and widened search parameters creates unprecedented opportunities for discovery in the coming decades. Perhaps the most significant development driving the future of techno-signature research is the dramatic expansion of observational capabilities. A new generation of astronomical instruments, both ground-based and space-based, promises to revolutionize our ability to detect subtle signatures of technology across interstellar distances. In radio astronomy, the Square Kilometre Array, currently under construction in South Africa and Australia, will become the world's largest radio telescope upon completion. With collecting area equivalent to 1 square kilometre distributed across thousands of antennas, this instrument will achieve sensitivity far exceeding existing radio observatories. For SETI applications, this translates to the ability to detect much fainter signals from greater distances, potentially bringing civilizations using radio technology similar to our own within detection range, even if they are not deliberately transmitting toward Earth. The SKA's unprecedented combination of sensitivity, wide frequency coverage, and massive computational backend will enable simultaneous monitoring of millions of target stars across billions of frequency channels. This represents a quantum leap beyond previous radio SETI capabilities, effectively expanding the searchable parameter space by many orders of magnitude. Artificial signals that might have been lost in noise or missed due to insufficient frequency resolution in previous searches could potentially be identified with this new generation of radio telescopes. Optical and infrared astronomy are experiencing similar revolutionary advances. The James Webb Space Telescope, launched in late 2021, provides unprecedented sensitivity and spectral resolution in the infrared portion of the electromagnetic spectrum. While primarily designed for conventional astronomy and exoplanet science, Webb's capabilities enable detailed characterization of exoplanet atmospheres, potentially detecting artificial chemical signatures or thermal anomalies indicating technological activity. Ground-based optical astronomy will be transformed by extremely large telescopes currently under construction, including the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope. With primary mirrors spanning 30 to 40 meters, these instruments will collect far more light than existing telescopes, enabling more sensitive searches for laser signals, planetary surface modifications, or other optical technosignatures. Their advanced adaptive optics systems will partially overcome atmospheric distortion, approaching space-based resolution for certain observations. For technosignature research specifically focused on exoplanets, proposed space missions like the Habitable Exoplanet Observatory, if approved and developed, would provide direct imaging capabilities potentially able to detect artificial light or other planetary scale modifications on worlds orbiting nearby stars. Such instruments might identify unusual reflectivity patterns, artificial illumination on night sides of planets, or spectral features indicating industrial activity, opening entirely new avenues for technosignature searches. Beyond specific instruments, the overall trend in astronomy toward larger digital sky surveys that repeatedly observe the entire visible sky creates enormous datasets amenable to technosignature research. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will image the entire visible sky every few nights for a decade, generating petabytes of data, capturing both steady sources and transient phenomena. This temporal dimension proves particularly valuable for identifying artificial signals that might appear only intermittently, or exhibit patterns inconsistent with known natural variability. The explosion in observational capabilities is matched by revolutionary advances in data processing and analysis. Machine learning and artificial intelligence have transformed how astronomers handle the massive data volumes generated by modern instruments, enabling detection of patterns or anomalies that might elude conventional analysis methods or human inspection. These techniques prove particularly valuable for technosignature research, where the signal characteristics cannot always be precisely anticipated. Supervised machine learning algorithms trained on simulated technosignatures can automatically scan enormous datasets for similar patterns, while unsupervised methods can identify statistical anomalies that stand out from natural backgrounds without requiring specific templates. These approaches have already been applied to radio SETI data, identifying previously overlooked signal candidates worthy of further investigation. As algorithms grow more sophisticated and computational resources expand, the ability to recognize potential techno signatures within astronomical big data will likely advance dramatically. Quantum computing, though still in its developmental stages, offers tantalizing future possibilities for technosignature searches requiring immense computational power. Certain signal detection and pattern recognition problems that remain intractable for classical computers might eventually yield to quantum algorithms, potentially expanding the searchable parameter space by many orders of magnitude. The democratization of SETI research represents another significant trend shaping its future trajectory. While early searches were limited to a handful of professional astronomers with access to major observatories, contemporary technosignature research increasingly engages broader scientific communities and even public participation. Open-source datasets, distributed computing projects, and citizen science initiatives have expanded the human and computational resources dedicated to the search. Projects like SETI at home pioneered this approach by distributing radio astronomy data analysis across millions of personal computers worldwide. Although that specific project concluded in 2020, its legacy continues in various distributed computing and citizen science initiatives. The Breakthrough Listen project, for instance, makes its data publicly available, enabling independent researchers and enthusiasts to conduct their own analyses alongside the professional science team. This democratization extends to hardware as well. The rapid development of small radio telescopes capable of conducting meaningful SETI observations at relatively modest cost has enabled university groups, amateur astronomers, and independent researchers to contribute to the search. Networks of such instruments distributed globally could potentially achieve significant sky coverage and observing time beyond what major observatories alone could provide. In optical SETI, advances in photon counting detectors and signal processing have similarly reduced the entry barriers for meaningful searches. University observatories and even advanced amateur facilities can now conduct observations capable of detecting hypothetical laser signals from nearby star systems, dramatically expanding the observer base beyond the handful of professional projects that dominated earlier decades. The future of technosignature research will likely witness further expansion of this distributed approach, with professional astronomers, academic institutions, private organizations, and citizen scientists forming an interconnected ecosystem, collectively searching across multiple modalities and methodologies. This diversity creates resilience and breadth typically lacking in more centralized research programs. The conceptual expansion of what constitutes a potential technosignature represents another crucial development shaping the field's future. Early SETI focused almost exclusively on deliberate radio transmissions, reflecting both the technological limitations of the era and the assumption that advanced civilizations would intentionally announce their presence through electromagnetic signals. Contemporary technosignature research encompasses a far broader range of potential evidence, from unintentional technological emissions to megastructures, from atmospheric modification to artifacts potentially present within our own solar system. This conceptual broadening acknowledges both our expanded detection capabilities and evolving understanding of how intelligence might manifest across cosmic scales and evolutionary timescales. Future searchers will likely continue this expansion, developing increasingly sophisticated frameworks for identifying potential technological signatures across diverse observational modalities. Rather than focusing exclusively on communication attempts, researchers will increasingly search for evidence of energy utilization, resource extraction, waste products, or other incidental indicators of technological activity. This broader perspective connects techno-signature research more closely with mainstream astronomy and planetary science, creating natural collaborations around topics like exoplanet characterization, galactic evolution, and solar system exploration. Such integration represents a significant shift from earlier periods when SETI operated largely independently from conventional astronomical research. Interdisciplinary collaboration will become increasingly central to techno-signature research as the field engages with questions spanning physics, biology, chemistry, computer science, anthropology, and philosophy. Understanding potential technological evolution requires insights from all these domains and more, necessitating research teams with diverse expertise. The astrobiology community has pioneered such collaborative approaches, bringing together specialists from numerous disciplines to address questions about life's origin, evolution, and distribution throughout the universe. This model increasingly extends to techno-signature research, with formal and informal networks connecting researchers across disciplinary boundaries. Future projects will likely institutionalize such collaboration through dedicated research centers, funded initiatives, and integrated training programs spanning multiple fields. From a methodological perspective, the most significant evolution in techno-signature research may involve the shift from assumption-driven to anomaly-driven approaches. Traditional SETI focused on detecting specific anticipated signal types, like narrow-band radio transmissions or laser pulses, based on assumptions about how advanced civilizations might communicate. While these targeted searches continue and remain valuable, they are increasingly complemented by more agnostic approaches that simply look for anything in astronomical data that cannot be readily explained through known natural processes. This anomaly-driven perspective acknowledges the limitations in our ability to predict the specific technologies, motivations, or evolutionary pathways of extraterrestrial intelligence. Rather than searching exclusively for techno-signatures resembling our own technology, these approaches remain open to evidence that might indicate entirely different technological trajectories or capabilities beyond our current understanding. The future balance between targeted searches for specific techno-signatures and broader anomaly detection will likely depend partly on resources, partly on results. Null results from increasingly comprehensive targeted searches might gradually shift emphasis toward more agnostic approaches, while interesting anomalies discovered through either methodology would naturally attract focused investigation. The interplay between these complementary strategies creates a robust overall research program combining the statistical rigor of well-defined searches with the openness to unexpected discovery characteristic of exploration-oriented science. This balanced approach maximizes the probability of detection regardless of whether extraterrestrial technology resembles our anticipated forms or manifests in ways currently unimagined. Funding represents another crucial factor shaping the future of techno-signature research. Historically, SETI has faced significant challenges securing consistent financial support, particularly from government science agencies. The field operated primarily through private philanthropy for many decades, with initiatives like the SETI Institute, the Breakthrough Listen Project, and various university-based programs relying largely on individual donors rather than conventional science funding channels. Recent years have witnessed a gradual shift in this landscape. NASA has cautiously re-engaged with techno-signature research, hosting workshops, funding limited studies, and acknowledging its legitimacy within the broader astrobiology research portfolio. Other space agencies and scientific funding bodies worldwide have similarly begun supporting projects that include techno-signature components, though often framed within wider exoplanet or astrobiology contexts, rather than as dedicated SETI initiatives. Private funding continues to play a crucial role, with philanthropic support from technology entrepreneurs enabling large-scale projects beyond what conventional science funding might support. The $100 million Breakthrough Listen initiative exemplifies this approach, providing consistent funding for a decade-long comprehensive search utilizing major observatories worldwide. The future funding landscape will likely feature increased diversity, with government sources, private philanthropy, corporate sponsorship, and crowdfunding all contributing to a resilient overall ecosystem. This mixed model offers advantages beyond mere financial stability, as different funding sources often enable different types of research with varying time horizons, risk profiles, and objectives. Government science agencies typically support methodologically rigorous programs with clear deliverables and connection to broader scientific objectives. Private philanthropy often enables higher risk, longer-term projects that might not fit conventional funding paradigms. Corporate involvement might accelerate technological development or data analysis capabilities, while crowdfunding can engage public interest and support specialized or unconventional approaches. The field's legitimacy within mainstream science continues to strengthen, reflected in increasing publication of techno-signature research in prestigious peer-reviewed journals, presentation at major scientific conferences, and integration within university curricula. This academic normalization creates pathways for career development that were largely absent for earlier generations of SETI researchers, attracting new talent and enabling longer-term research programs. As younger scientists enter the field without the historical baggage that sometimes accompanied earlier SETI efforts, techno-signature research increasingly operates as a normal scientific discipline rather than an exceptional or marginalized pursuit. This normalization benefits both the researchers and the research, enabling standard scientific practices of hypothesis testing, methodological refinement, and theoretical development to advance understanding regardless of whether detection occurs in the near term. The relationship between techno-signature research and the public represents another important dimension of the field's future development. SETI has always captured popular imagination more intensely than many scientific disciplines, reflecting the profound human interest in questions about our cosmic context and potential extraterrestrial neighbors. This public engagement creates both opportunities and challenges. On one hand, widespread interest supports funding, volunteer participation, and broader societal value beyond specific scientific results. On the other hand, media coverage sometimes sensationalizes the research or creates unrealistic expectations about imminent discovery, potentially undermining scientific credibility when dramatic announcements fail to materialize. Future techno-signature research will likely pursue more sophisticated public communication strategies that maintain popular engagement while accurately conveying the scientific process, methodological challenges, and realistic probabilities. Effective communication not only supports the field's sustainability, but also contributes to scientific literacy more broadly, using questions about extraterrestrial intelligence as entry points for explaining fundamental concepts in astronomy, biology, information theory, and other disciplines. Education represents another crucial aspect of this relationship. University courses, online learning platforms, and informal educational initiatives increasingly incorporate techno-signature science, training future researchers while enriching public understanding. These educational efforts often emphasize the interdisciplinary nature of the field, attracting students from diverse academic backgrounds and preparing them for careers spanning conventional disciplinary boundaries. The long-term sustainability of techno-signature research depends significantly on developing these educational pathways and creating career opportunities for emerging scientists interested in the field. Graduate programs, postdoctoral positions, and faculty appointments specifically supporting techno-signature research have historically been limited, but are gradually expanding as the field gains scientific legitimacy and funding stability. Looking beyond methodological and institutional developments, perhaps the most profound question facing future techno-signature research involves its relationship with our evolving understanding of intelligence itself. As artificial intelligence advances rapidly and our conception of cognitive diversity expands beyond traditional anthropocentric models, how might our search for extraterrestrial intelligence evolve? Future techno-signature research will likely incorporate increasingly sophisticated understanding of potential intelligence modalities beyond those characteristic of human cognition. This might include consideration of distributed or collective intelligence, hybrid biological synthetic systems, or computational entities operating on timescales and through mechanisms fundamentally different from biological cognition. Such expanded conceptions of potential intelligence would inform both what we search for and how we interpret potential detections. For instance, communication patterns optimized for artificial intelligence might differ substantially from those designed by or for biological entities, featuring different timing structures, information density, or error correction mechanisms. Similarly, the technological footprints of predominantly synthetic intelligence might emphasize computational efficiency, thermodynamic optimization, or resource utilization patterns distinct from those of biologically originated civilizations. The coevolution of artificial intelligence with techno-signature research offers particularly interesting possibilities. Machine learning not only supports data analysis, but potentially provides insights into how non-human intelligence might manifest observable signatures. As our own AI systems grow more sophisticated, they might help us imagine and model cognitive and technological trajectories significantly different from humanity's developmental path. This conceptual broadening carries significant scientific advantages, expanding the range of potential techno-signatures considered and reducing the risk of missing evidence due to overly anthropocentric assumptions. It also reflects intellectual humility regarding the potential diversity of intelligence in the universe, acknowledging that our own evolutionary path represents just one of countless possible trajectories through which cognition capable of creating technology might emerge. The time dimension of techno-signature research deserves particular attention when considering its future. Unlike many scientific disciplines where discoveries typically emerge relatively quickly after new methods or instruments are deployed, the search for extraterrestrial intelligence operates on potentially much longer timescales. Negative results from even the most comprehensive searches cannot definitively answer the question of whether technological civilizations exist elsewhere, only constrain their prevalence or characteristics within the searched parameter space. This temporal challenge requires both scientific patience and institutional structures capable of maintaining consistent effort across decades or longer. The most successful future techno-signature research programs will likely combine near-term achievable objectives with longer horizon aspirations, creating sustainable progression regardless of whether definitive detection occurs quickly or requires generations of progressively more sophisticated searching. Within this extended timeframe, incremental advances in methodology, technology, and theoretical understanding contribute meaningful scientific value regardless of whether the ultimate question is answered. Each constraint on the distribution or characteristics of potential techno-signatures refines our understanding of cosmic evolution and the developmental trajectories of complexity. Each new search capability expands our perspective on what might be detectable and how intelligence might manifest observable signatures. The integration of techno-signature research with broader investigations of cosmic evolution creates particular scientific value resilient to continued null results. By examining questions about intelligence and technology within the wider context of chemical, biological, and cultural evolution, researchers develop insights applicable across multiple domains, regardless of whether extraterrestrial technology is ultimately confirmed. What would the confirmation of a techno-signature mean for the future of the field and humanity more broadly? The detection of unambiguous evidence of extraterrestrial technology would trigger not only the most profound scientific discovery in human history, but potentially transformative cultural, philosophical, and even technological consequences. Scientifically, confirmation would immediately shift research emphasis from detection to characterization, with enormous effort directed toward understanding the nature, capabilities, location, and potential communicative intent of the detected technology. The specific type of techno-signature detected would heavily influence subsequent research priorities, with different implications emerging from a radio signal versus an atmospheric techno-signature versus evidence of a megastructure. Beyond science, confirmation would catalyze unprecedented philosophical reconsideration of humanity's cosmic context. The knowledge that technological civilization had emerged independently elsewhere would fundamentally reshape our understanding of cosmic evolution and the prevalence of intelligence. Depending on the specific characteristics of the detected technology, this discovery might suggest paths forward for human technological development or indicate potential existential challenges technological species typically encounter. While continuing null results cannot prove absence, they progressively constrain the parameter space within which technological civilizations might exist. Each more sensitive search that finds nothing tells us something about the prevalence, characteristics, or developmental pathways of technology in the universe. This accumulating knowledge, even without definitive detection, advances our understanding of cosmic evolution and the context for humanity's own technological development. The future of technosignature research thus offers meaningful scientific advancement regardless of detection outcomes. If we discover clear evidence of extraterrestrial technology, we gain unprecedented insight into one of humanity's most profound questions. If comprehensive searches continue to find nothing, despite dramatically improved capabilities, we gain progressively stronger constraints on the prevalence and characteristics of technological intelligence in the cosmos. In either case, the search itself advances human knowledge, technological capabilities, and conceptual frameworks for understanding intelligence and its manifestation across cosmic scales. This inherent scientific value, independent of ultimate detection outcomes, ensures the field's continuing relevance even as specific search methodologies evolve in response to new capabilities and theoretical insights. As we move deeper into the 21st century, technosignature research stands at a moment of unprecedented opportunity. Convergent revolutions in observational astronomy, computational capabilities, and theoretical frameworks enable searches of scope and sensitivity unimaginable to the field's pioneers. Whether these expanded capabilities lead to detection or progressively stronger constraints, the scientific journey continues, driven by one of humanity's most enduring questions. Are we alone in our capacity to wonder about the stars and create technology to understand them? As our exploration of humanity's search for technosignatures draws to a close, we find ourselves returning to the fundamental questions that have driven this quest since its inception. In the vast silence between stars, in the subtle patterns of light from distant worlds, in the chemical fingerprints of alien atmospheres, we have sought evidence that somewhere, somehow, minds not unlike our own have gazed upward at different skies and wondered similarly about the cosmos. This search represents something profound about our species, a willingness to extend our questioning beyond planetary boundaries, beyond biological kinship, toward a potential communion with intelligences that may bear no physical resemblance to ourselves, yet share the fundamental experience of wondering about their place in the universe. Whether conducted through massive radio telescopes scanning the heavens for artificial signals or space-based observatories analyzing the light from distant planets, this quest transcends mere scientific curiosity to touch on our deepest existential questions. The methods have evolved dramatically since Frank Drake first pointed the Green Bank telescope toward nearby stars in 1960. What began as a limited search across a narrow band of radio frequencies has expanded into a multidisciplinary enterprise spanning the electromagnetic spectrum and beyond, incorporating insights from disciplines ranging from astronomy and biology to computer science and philosophy. Technologies unimaginable to those early pioneers now sift through petabytes of data, identifying patterns and anomalies that might indicate the presence of minds restructuring their corners of the cosmos through technology. Yet despite these remarkable advances in our search capabilities, the stars have remained silent, or at least have not spoken in ways we have definitively recognized. The skies above continue their age-old patterns. The planets we discover around other stars show no unambiguous signs of technological manipulation, and our radio receivers record the hiss and crackle of natural cosmic processes, rather than the structured patterns that would announce another technological species. This silence itself carries meaning, constraining the possible distribution and characteristics of technological civilizations within our galaxy. Each observation that reveals no obvious techno-signature tells us something about the rarity, remoteness, or nature of technology in the cosmos. The absence of detected Dyson spheres suggests limits on the prevalence of civilizations capturing entire stellar outputs. The lack of confirmed radio signals constrains the commonality of species using electromagnetic communication similar to our own. The apparent absence of large-scale engineering visible through our telescopes bounds the frequency of civilizations reshaping their environments in ways analogous to our emerging capabilities. Yet these constraints remain provisional, limited by the narrow slice of the vast parameter space we have been able to search thus far. Our instruments peer through keyholes of time, frequency, and sensitivity, potentially missing signals that fall just beyond our current capabilities or manifest in ways we have not anticipated. The vast majority of potential techno-signatures remain unexplored, awaiting more sensitive instruments, more sophisticated algorithms, or conceptual breakthroughs that might reveal what has been hidden in plain sight. For all the technological sophistication of our search, we remain profoundly limited by our imagination and experience. We necessarily seek what we can conceive based on our own technological trajectory, our own cognitive frameworks, our own evolutionary path, from planetary life to questioning intelligence. Yet intelligence that evolved under different conditions, with different physical constraints and evolutionary pressures, might create technologies and techno-signatures that operate outside our anticipated parameters. This limitation reminds us of the inherent humility required in this search, an acknowledgement that we may be like early humans on a shoreline, searching the horizon for familiar smoke signals, while missing the sophisticated sonar communications of cetaceans swimming beneath the waves. The history of science teaches us that reality often exceeds our conceptual frameworks, revealing phenomena and principles beyond our initial imaginings. The search for techno-signatures may well follow this pattern, eventually finding evidence of intelligence in forms we have not yet learned to recognize. Despite these challenges, the search continues and expands. New telescopes scan the heavens with unprecedented sensitivity. New algorithms sift through astronomical data, identifying anomalies that warrant closer investigation, and new theoretical frameworks broaden our conception of what might constitute evidence of technology. Each advance incrementally expands the searchable parameter space, gradually illuminating the cosmic ocean within which technological species might exist. This persistence reflects something fundamental about human nature, our unwillingness to accept cosmic solitude without thorough investigation, our determination to find whether our capacity for abstract thought, technological creation, and existential questioning is unique or shared across the stars. It represents a form of cosmic optimism, a belief that the conditions that led to our emergence might have been replicated elsewhere, creating potential companions in our quest to understand the universe. The search for techno-signatures also connects us with our own future in profound ways. As we develop frameworks for detecting evidence of technology across interstellar distances, we inevitably reflect on what traces our own civilization might leave for others to find. The radio transmissions, space probes, atmospheric alterations, and potential future engineering projects that constitute humanity's techno-signatures form a kind of cosmic footprint, an announcement of our presence that expands outward at the speed of light. When we search for evidence of others, we are in essence looking for mirrors of what we might become, civilizations that have perhaps navigated the technological transitions we now face and developed sustainable relationships with their planets and technologies. This creates a unique temporal symmetry in the search, as we simultaneously look for civilizations that might be thousands or millions of years more advanced than our own, while considering how civilizations at earlier stages similar to humanity's current position might become detectable across cosmic distances. This connection between past, present, and potential future gives the search for techno-signatures a significance beyond its immediate scientific objectives. It becomes a meditation on the longevity and cosmic impact of technological intelligence, on the challenges species like our own might typically encounter as their capabilities grow, and on the possible developmental trajectories that might lead towards sustainable presence within a galaxy, or toward transient flashes of technology that fade back into the cosmic background. As you drift towards sleep beneath this canopy of stars, consider the possibility that somewhere, minds not unlike your own might also be listening, watching, wondering about the same questions that have occupied human thought since we first developed the capacity to contemplate our place in the universe. Perhaps they have developed technologies beyond our current imagining, reshaping their corner of the cosmos in ways we might barely comprehend. Perhaps they have followed developmental paths that diverge dramatically from humanity's trajectory, creating civilizations with fundamentally different relationships to their planets and technologies than those we have established. Or perhaps we are alone in our current questioning, the only technological species currently active within our galaxy, or at least within our detection range. This solitude would not diminish the significance of our search, but rather highlight the profound responsibility humanity bears as potentially unique carriers of technological intelligence and abstract thought within our cosmic neighborhood. If we are indeed rare or alone, the questions we ask, the knowledge we accumulate, and the future we create carry even greater significance as potentially unique expressions of the universe coming to know itself through conscious investigation. The path forward remains open to discovery, to unexpected findings that might fundamentally reshape our understanding of intelligence and its distribution throughout the cosmos. Each silent observation incrementally constrains the parameter space within which technological civilizations might exist, while simultaneously driving the development of more sensitive detection capabilities that expand the boundaries of what we might discover. In this continuous cycle of searching, constraining, and searching again with improved capabilities, we participate in one of humanity's grandest scientific endeavors, a quest to determine whether our capacity for technological creation and abstract thought represents a common outcome of cosmic evolution or an extraordinary rarity. The answer, whether it comes through confirmed detection or progressively stronger constraints on prevalence, will profoundly influence our understanding of humanity's context and potential future. As our exploration concludes, the skies above remain as they have been throughout human history, filled with points of light that have inspired wonder across countless generations. Yet our relationship with those distant stars has fundamentally changed through our developing scientific understanding and technological capabilities. What once seemed eternally inaccessible now becomes progressively more knowable. The composition of distant atmospheres, the properties of planets orbiting other suns, and potentially the activities of minds reshaping their worlds through technology. Whether we ultimately discover clear evidence of extraterrestrial technology or find that technological intelligence remains elusive despite our best efforts, the search itself transforms us. It expands our perspective beyond planetary boundaries, reminds us of our participation in cosmic processes that transcend individual or even species lifespans, and connects our questioning with the fundamental creative forces that have shaped the universe since its beginning. Sleep now, beneath these ancient stars, knowing that your wondering participates in humanity's greatest questioning, an extension of curiosity beyond our immediate environment toward the possibility of minds that might share our fundamental experience of observing, wondering, and creating tools to extend understanding beyond biological limitations. In that questioning, in that patient listening to the silence between stars, we realize one of the most profound expressions of what it means to be human, to reach beyond ourselves toward potential communion with the unknown.